Hello, hello, hello. How is everybody doing? This was a late start for us tonight. I apologize. Welcome to SkyTour LiveStream. This is the first all-new SkyTour LiveStream of 2019. We're going to talk about some cool things tonight, too. And we're going to also talk about some of this stuff when we get to our show Sunday as well. Remember, Sunday is the first 2-hour show, and it will start at 8 p.m. Eastern Time on kgraradio.com. And you join us, and if you're in the chat and you have questions, we'll actually take questions during the show as well. Now that we have the time, now we can actually spend a lot more time in the chat and hang out with you guys a little bit more dynamically than we have been. I want to welcome you guys here. Thank you so much for jumping in here on New Year's Day. The screen right now has the planetarium system on it that we're using in the new SkyTour. But we're in Orion right now, and if you want to check out what that looks like, well, then I just have to take us over to that particular screen, and we'll see it in a sec. All right, so here is the all-new SkyTour. Little issue there. I got to remove right there. Okay, here we go. So now we should have it should be showing just fine. Okay. You'll notice also that I have one camera over here that's not quite working. That's because the batteries have died, and I will be replacing the batteries soon, maybe during the course of the evening here. But this is the Orion Nebula. We looked at it the other night. The things that have changed here on the screen are only that I've moved the dome ops view to the lower left. I did that because it's actually better, and this way I have telescope view over here. I have the dome ops view down here. The live view is here, and then we have the camera and the cameras, the dome cameras over here. I think this will be a little better, but either way, none of this stuff gets in the way when we want to actually look at anything. Because we will be closing in on it and looking at it closely. Now, if I, over here in this main view, I want to go into a focus view. This view is going to help me just make sure that we have good focus. And we do. This is a magnified view of the trapezium, the 4 bright stars in the middle of the Orion Nebula. And these 4 bright stars are young and hot, spewing ultraviolet radiation. And this, I have this set up right now to look like it looks in a like a 4-inch telescope. If you were to get a 4-inch telescope, this is what the Orion Nebula would look like. Now, in a telescope that's a little bigger than a 4-inch telescope, then it might look a little brighter. It might look more like this. Okay, this is how it may look in such a telescope. All right. And let me just turn off the close-up view. So this is kind of what it might look like. And that green is rather telling because the green is not what the nebula's color is, but that's the, since there are more than one color coming from that nebula, they do affect the part of your eye that is a receptor for the green light. This does not have anything to do with why there's no green stars. Now, the other night, somebody had asked, and Daryl actually was putting in some links, which are really helpful if you followed them. The green stars, the reason we don't see green stars, has to do with the way stars radiate. I mentioned that, but to be a little bit more detailed about it, it has to do with what's called a Planckian, or like after Planck, Planck. And Planck discovered that there is a radiation curve that stars at different temperatures will emit. That radiation curve is called a black body. And within the black body, you have red, you have orange, yellow, and blue. And you don't have indigo and violet, okay? And yes, there's a few clouds passing over the Orion Nebula just there. You don't have blue, you don't have indigo and violet, but you do have blue, you do have orange, you do have yellow, and you do have some red. But there's really no green in the Planck part of the curve. for this. So the green is a little farther away. I mean, it's very, very close. And you can actually see a apparent green color, and that has to do with your eyes and the way your eyes are reacting to things. All right, so that's really what's happening there. This green is, again, just due to the camera sensor. If I was actually, if I take this, if I shut off this, we take this, we'll shut off the movie mode, okay, the 4K video, and let's drop this down to, say, let's go to, let's say 10,000, okay? Now, there might be some clouds. Let's do 10 seconds at 10,000, okay? And now let's take this picture. So now for 10 seconds, we're taking in light. The light is coming in from this location, and it's hitting the sensor, and it's accumulating on the sensor. So this is very different from how your eyes view things, okay? And that's what we're seeing here. This is the Orion Nebula in its proper colors. You see this? And we see this reddish hue here. We see this blue hue here. Now, the Orion Nebula is known as an emission-reflection nebula. It's not one or the other. It's actually both. And so many nebulae are exactly that, all right? So I know, for instance, that if we look at the Orion Nebula in, let me just zoom in a little bit here, actually, and let's see if we can get a little closer. So if we look here, we'll see that this color here is definitely a bluish color, all right? This is blue in here as well because there's a lot of dust in here. This isn't gas that is blue. This is actually reflections off of interstellar dust. The interstellar dust is reflecting the light from hot stars. And then this red part, these red parts over here, these are areas that are a little bit different, same as this here. These are areas where the light is from these stars is causing the hydrogen gas in this region to ionize, and it excites the hydrogen gas. And the electron, there's only one electron on a hydrogen atom, remember. There's a proton in the center and an electron on the outside. And you can get sometimes a proton with a neutron, and that'll be a deuterium atom, okay? But hydrogen atoms have one electron. They'll never have two electrons. So when that electron jumps off the hydrogen atom and disappears, it's now free of the hydrogen atom out here. And then all of a sudden, as the electron bounces into other objects out there and other electrons, it loses some energy. And when it does, it falls back down into the nearest hydrogen atom, and that's called recombination. And when that happens, it gives off a little energy, and that energy is in the form of a red light, the characteristic red light. This is the light of what we call hydrogen alpha. All right, and so this is a hydrogen alpha region. We also call it H Roman numeral 2, H, H2 region. And why that? Well, because H Roman numeral 1, or HI, okay, H1, is a hydrogen that has no net charge. What's that mean? It means it has its proton and it has its electron. It's the normal ground state of the atom. But when it ionizes and loses that electron, it's ionized. That ionization process now makes it a net positive charge, and we call it an H2, or H Roman numeral 2, for this ionized hydrogen region. And it takes a lot of energy, a lot of energy from these stars to cause this light to be ionized, or causing this hydrogen gas to be ionized. But again, in the middle of it all, we have dark dust. This is dust, okay, that's in this nebula. And this is actually encroaching and between us and the brighter parts of the nebula behind it, you see? So this is actually the closest thing to us compared to these things back here. So it's in front, and the stuff's in the back. We see a lot of that in the universe. But because it all looks two-dimensional, we tend to think, well, this just is black, empty space. It isn't. It's actually just dark matter, dark material, all right? That's in between us and the brighter part of the nebula. If this wasn't here, we'd see a continuous little bubble here of this reflection nebula and then the emission nebula, this orange or reddish stuff. So you see, that's how these nebulae work, and these nebulae are really, really, really wonderful places where stars form. I'll tell you the other thing too. Deep in this nebula, somewhere in this region and over here and out over here, there's actually areas in the nebula where we can see shock waves that come from stars that have very powerful stellar winds, and they blow a bubble basically. And that bubble doesn't come from them. Their stellar wind is pushing material out, gas and dust. And that gas and dust will collide with other things in the interstellar medium. And that's how it becomes visible to us, because sometimes that process causes this ionization process, and we'll see them glow, or we'll see sharp-edged objects that, like this, okay? Sharp-edged objects that are the result of impact, a flow from one direction to the other. This is a flow going one way and hitting something else that's there, and it forms this semi-rigid line. But just like with clouds, the closer we get, and this is not a really good, not a good way to show it, but just like with clouds, the closer we get, all right, these areas that that would be previously very sharp, when you get closer to clouds, you find, well, they're actually kind of soft at the edges and soft inside, and you don't even realize you're passing into them until you're in them. Same thing here. It's just that this is so far away. This is about 1,300 light years away, and this distance here from here to here is actually about 30 light years. So it's not bad. Okay, and in terms of the sky, why don't we take a look at that, because I want to show you what that means in terms of the sky. So we're going to go over to our stellar cartography section, and we're going to take the Orion Nebula here, and I've got a little tool that I've added to this, and it looks like this. Basically, if I click and we drag a line, this will tell us right here how big this area is, and it's actually 50 minutes of arc across. And at 1,300 light years away, you can then use this to calculate how big the nebula is. This is kind of cool. So if you want to know how far away or how far apart two stars were, let's say this star here and this star here, we could say, well, let's take this and we just measure over to this, all right? And now we know, all right, that it's 1 degree, 48 minutes, and a few seconds far apart from each other. Now, knowing what this star has and what this star has, or what this star is, and how far apart it may, what kind it might be, let's click on it. All right. Okay, its distance is 1,342 light years. You can see it over here on the left. All right, and then this star over here is 2,329 light years away. So you can see this star is actually much farther. Okay, actually more than twice as far as this star. Again, the universe is in 3 dimensions. So the actual separation, you see, is a mathematical calculation. We can figure the angle apart, and based on how far apart they are from each other and how far they are from us, we can figure how far they are from each other in terms of real light years. We're not going to do that. We actually have done that before with double stars and calculated the separation. And it uses something called the small angle equation, but that wouldn't be how we wouldn't use that for this. But just give you an idea, we have such a bunch of really interesting stuff at our disposal to use here. So this is a cool application that would help us and will help us to figure things out. Now, just as a little reminder, you can see where the scope is pointing. This is off a little bit. Right now we're looking here, and the way we know that is just by going to our main view, okay, and we can see that this is the Orion Nebula here. Yet when we go over to the planetarium view, okay, we see that we're not near it. So this is a matter of just getting the telescope coordinates. I have to go out in the dome and do it. I did it earlier tonight, and in my haste, I didn't do it quite right, but that's okay. No, don't worry. I can get to it. I'll know where we are, and I'll be able to show you where we are. It's not going to be a problem. So this square, remember, is, and if I close in, you'll see this square is 1 degree and 16 minutes across, and it is about half a degree wide, like this. Okay, it says by 51. Well, actually, that's a little too big. Actually, that's not right. The point being that this is a mathematically calculated rectangle based on the size of the sensor in the camera that we have. And speaking of cameras, I've added a second system to the SkyTour LiveStream lineup. And this is a really cool system that I want to show you. I think that you'll appreciate what it does. And it starts by going here. This is the view of the Orion Nebula I took earlier, showing the interesting colors within the nebula. This is a spectrum of the Orion Nebula. Very interesting. We're going to be able to use this a lot more and do some really cool work with the spectrum. Sorry about that I'm doing that. I'm not trying to. And so when we get to do more of these, I'll show you how we can actually determine what the stars and nebulae are actually made of by looking only at their spectra. So I've added a spectral system. It's a whole second system on top of the telescope. In fact, in the dome view, dome cam, I think it's dome cam 1. Let's go see. In dome cam 1, you can actually see the camera. It's right. Let's see over here. You can actually see the spectral camera. It's right here. This is it. This is the edge of it. Okay. So there's a spectral camera. You're looking on the right side of the view here. So this is the spectral camera, and this is the main telescope body right here. This fabric-y looking thing is actually a wrapper that I've put around the end of the telescope so that we will no longer have to worry about ice forming on the front lens. It's called a dew zapper, if you would, and it makes sure that we don't get any moisture, keeps the telescope nice and dry, and it's not a lot of current, not a lot of heat, but just enough to keep that dry. And it only has to be just a couple degrees above the ambient freezing temperature, and we won't get any moisture on the lens. And that's a really good thing, because that would shut down, and has shut down, our streams very, very quickly. So this is sort of the look and feel again, and also this system here I think is the one that we're going to have a lot of fun with. Actually, for fun, let's just take a picture. If you look on the left here, you'll see I have a 10-second shot set up. Cloudy doesn't mean cloudy. Cloudy it just has to do with white balance, and I just want to make it Kelvin. So now what I'll do is we're going to take a photo, and I've already pre-focused it because the camera is in manual mode. All right, and I pre-focused this so that we will have a really interesting photo. Now, 5000 ASA, or ISO as it's called. ISO stands for International Standards Organization, and it's just an established sensitivity scale that we use for this. And by the way, I just want to make sure that Amanda's still with me. Are you still here, Amanda?
I am here.
Oh, okay, very good. I wanted to make sure, because Amanda's a little under the weather tonight, folks. So, she still, the dedication is immeasurable with her. She still wanted to be here anyway, even though she's not feeling up to her tip top. So, show her some love, folks. As
I'm still monitoring chat, so if you guys have any questions, I will make sure to get them to Mark.
Thank you. Yeah. So let's take this picture
And Happy New Year to everybody. Thank you for stopping by on this first day of 2019.
Yeah, and what a day it was. I saw the New Year come and go, and about a half hour later is when the real fun started, because that's when the New Horizons spacecraft reached closest approach to Ultima Thule, which is a a little tiny, well, an icy body that almost could be a binary asteroid type thing. It looks like it's two objects that are very close together, maybe linked across the center. And by the way, I'm taking a photo here so you can see what happens. It's going to be a 10-second photo of the sky using this spectral camera. So you'll see a new spectrum show up here in a bit. And Ultima Thule is only 30 kilometers across. But some intrepid folks actually managed to get images of Ultima Thule passing in front of certain stars. And just as predicted, you saw Ultima Thule knock out these stars. It was so cool. Very cool. So here's another spectral view. Now the view, it will take some getting used to, and we'll talk about it as we move into the whole world of spectra. But the thing that I want you to be interested in is when we look at these bands. Now this is really narrow, and there's a way that we can actually make this a lot better. So I'm going to actually go to our control program right now, and I'm going to do this. I'm going to turn off. See this right here? I'm going to turn off the tracker. All right? I'm going to turn off the tracker. And when I do that, now the telescope is no longer using its drive. Now when I press and take another photo, okay, now we're going to see a very different spectrum. We're going to see a spectrum that's a little wider because we're allowing it to get a little bigger. We're letting it drift. And by drifting, we're going to get this wider spectrum, and that'll be easier to analyze. And I think that will be a very, very cool process. And there you go. So now you can actually see this difference in the spectrum. All right. So we're tracking again. But if you notice now, for instance, we come down and say we look at this. We look at this guy right here. Okay. This, you can actually see now. You can see how there's some divisions in here. There's some interesting lines that are appearing in here. And that's just a star image. Okay. And for the hot blue stars, you'll notice that the blue sections are actually very, very bright. And what are we looking at? We're actually looking at the black body radiation curves is what these are called. Stars radiate as what are called black bodies. And that is it's a certain set of radiations that we can see coming from a star. And there was a scientist named Wien, W-I-E-N, and he came up with a law which shows that for a particular, basically, color of a star, it's going to be a certain temperature. And that was very, very important in the way we classify things in astronomy. This particular scene, we have some dim stars in here as well, but let's just go to a little bit brighter location and take another set of spectra, because I think it'll be pretty cool. So we're going to go and do that right now. And the way we're going to do that is I'm going to go back to our planetarium program and find ourselves a new location to go to. All right, so here's what we're going to do. We're going to pull out of this, and let's just move us up to, let's say, here, right around Alalam. Let's try that. Okay, so we're going to go to about right near Alalam. All right, so we're moving the telescope now, and you'll see the little yellow thing come up. And if we go to our actual live view, you'll see that we are moving, and you'll see that it's moving just now. All right, and just coming into view. And that's excellent. So now, with the additional stars that we're seeing in here, I have a feeling that we're going to be able to capture a couple of interesting spectra. So what I'm going to do is go back to our other setup here, and we're going to take another photo. And this photo is going to, again, show us some value added. And I suspect that the stars that we'll see will be a little bit brighter. That's what I suspect. I may have to up the exposure a little bit, because I'm actually this this opening here is a little bit fainter. It looks like meteors, doesn't it? You know, the opening's small. It's much, much smaller. Okay, so you can see how bright these are. Okay, but one thing that you don't notice, right off the bat, is you don't see that it's broad and wide anymore. And so what I have to do now is, and I'm actually going to move us up a little bit more too, actually. Let me just do that right now. Well, these are all the applications I run. So what we're going to do is go to here, and I'm going to bring us back out and take us up to about here. Just a little more. Maybe there. Let's see what we get, because we're going to move the telescope up there. All right. And by doing that, we're going to end up seeing a few new objects that are possibly going to be in our view. Remember, this view here is magnified. So we're with this other camera, we're actually looking at a much, much larger field of view. In fact, several degrees. This camera here, we're only looking at 1 degree across and half a degree top to bottom. So it's a much smaller area. The full moon would basically fit in this frame, and that's the kind of size of the area that we're looking at, which is kind of neat. Yep.
We have a question, and
Sure.
I'm sorry, I must have zoned out because I missed it, and it was going back to what we just passed yesterday.
Oh yeah.
There's a question in regards to that. I can't pronounce the name of the object, the Kuiper Belt object.
You can't?
No, I forget the name of it. I only heard about it yesterday from you, actually, on Facebook.
Yeah, no.
And then Daryl was mentioning it, and yeah, I can't remember the name of it.
No, New Horizons, had just a record run here. Oh, this is beautiful. This is Orion's Belt. 3 stars of Orion's Belt. And the record run with this was that we finally managed to get the closest. Well, we got to the farthest reaches of our solar system we've ever gotten to, and we reached this.
I know, but that doesn't make sense, because once we passed Pluto, wasn't every inch a new record on the furthest?
Absolutely. But this is, you got to understand, these objects, although there's millions of them, Ultima Thule, which is the object we reached, was 2,200 miles from the New Horizons spacecraft at the time. So we actually got out to Ultima Thule and passed closer to Ultima Thule than we did to Pluto. But Ultima Thule is only 30 kilometers across. Pluto's a lot bigger, so Ultima Thule is going to look small in the imagery that is produced. But it's really, again, it's actually a very cool, very neat process by which we got out there, because New Horizons, just by chance, was being brought close to Ultima Thule. Okay? There was no reason to expect that it would actually be in line with anything. But when they analyzed the paths and the orbits of these objects out there, remember, Ultima Thule actually wasn't discovered until somewhat recently. And when they found it, they said, hey, let's see if we can get New Horizons to go there. And they did. And it was really cool how they managed to approach Ultima Thule and but pass it and do that flyby, just like they did to Pluto. And think about this. Pluto was a dim, fuzzy object for a century practically, right? And then it became very, very clear what it was. It has an atmosphere, tenuous at best, a nitrogen atmosphere based on the nitrogen ices on its surface. And Ultima Thule, is something that doesn't have the same type of surface, no doubt. It could have similar ices, no doubt. But it is going to be a frozen object, and it is going to be very, very cold out there, because the Kuiper Belt is an area where there's very little sunlight. So the objects that are photographed out in the Kuiper Belt are objects that actually have to be photographed for a longer period of time because they're very dim. It's like being in a dusky twilight all the time. That's how far away from the sun they are. So, the farther we get from Pluto, we're actually, Ultima Thule is over 1 billion miles further than Pluto. Can you believe that? 1 billion miles further from Pluto.
Wow.
And by the way, Brian May, who is the Queen lead guitarist for the band Queen, Brian May is actually not an astrophysicist. I don't know if you knew that. You're the musically inclined one.
I was gonna say, what kind of segue was that?
Well, no. I don't need a segue,
okay,
but
why not?
hang on.
I thought I heard something to the contrary. Is this
No.
a rumor you're busting right now?
No, he's an astrophysicist.
Okay. Oh, I thought you said he was not.
Oh, no,
No,
he is.
yes, I thought he was as well. I thought I heard that before.
Oh, yeah, he's definitely an astrophysicist. I'm going to move us
That's
down
very
a little
cool.
bit. Yeah, and I'm very pleased that he actually wrote a song for New Horizons, and it was very cool because the song is called, of course, New Horizons. Great song. I, of course, bought it yesterday and listened to it about 1,000 times. It's like way too many times. But it is really, really, really good, and I really enjoy it. And it was nice to hear him and what he did, because I think that the song itself is just spectacular, and it celebrates our what is it? It celebrates our ability to go out there and find all the answers. Stephen Hawking's on the song. I mean, it's kind of cool. So if you get a chance, download, listen to, grab onto the song. It's really nice. It's a good song, and it's a lot of fun.
Cool.
Yeah.
I might look for that while we
Yeah.
move on to the next subject. But
Yeah.
before we switch topics,
You have a question, I think.
the question in question indeed.
All right.
Okay, and this one's from Daryl, so it's a good one.
Awesome.
Why are transmission rates so low from New Horizons and other distant spacecraft? Transmitter power, antenna size, distance.
Well, okay. What Daryl's asking is why is it taking so long to get this stuff? Maybe not why is it taking so long, but why?
That's my question. Why is it? I figured.
Well, I can tell
we'd
you that.
start getting
but
stuff already. I thought we did get stuff
we
already.
We are.
Yeah. Okay.
But here's the thing. The energy budget, when you get far out from the sun, the energy budget is affected by the cold and by other factors. For craft that use solar panels, then there could be a problem if there's no sun to provide power. Okay. Now, the New Horizons spacecraft, I don't think has solar panels, but I think that its power source, tried and true, is probably being tested to the limits. So they're being very careful, because if something goes wrong that far away, there's just, it's lost. Forget it. We're done. So the transmission rates are probably, set to be, such that they're not making the full burst transmissions because they don't want to go through their power budget for the day or whatever. I'm not sure how they manage that, and that's kind of a black box for me too. I'm not an engineer, but the engineers have some really neat solutions to these problems. But I don't. And to answer your question directly, Daryl, I'm really not sure why these probes have a lower data rate. But you also have to remember about when they were launched. Okay. Probes today are very different from probes 15, 20 years ago, which is kind of when New Horizons was launched, right? I mean, New Horizons was on its way to Pluto for, 15 years? So, I mean, things have changed over the years. So, clearly, New Horizons is benefiting from the technology of today. It's the technology of yesterday. So, that's probably one factor, I would think. But I don't know. I think that New Horizons also has given us quite a beautiful sampler already.
And what is driving it forward? You said you didn't think it had solar panels on it. it can't still be gas or fuel or whatever. Is it just floating, free floating now?
Well, I mean, it's in a coast phase for sure. It can do course
Yeah.
corrections. It does have the ability to make course corrections using, some amount of some type of onboard fuel. I'm not sure what, but I do think that it's probably a. We're also looking at it's probably a nuclear power system of some kind, just like we use for Cassini, But I'm not sure. I don't pay attention too much to that part of things. I'm okay with not knowing much of that. I don't really need to know what's happening there, but I do know.
And that's the thing.
Yeah.
I figure if you know something about it, you know everything about it, and I'm just
I
gonna
don't.
ask
Well,
all
I
sorts of
don't.
questions whether you know it or not. And I feel
That's
bad. I
okay.
don't mean to put you on the spot.
No,
I mean,
but
if you
you're
don't
not.
know, you
You're
don't know,
not.
obviously. But
I don't profess to know everything, and that's okay. I'm fine
I
with
certainly
that.
don't know everything.
Well, not
But
many of us do. There's not a lot of us that know everything. I don't think there's anyone that knows everything. But I do find that when we went by Ultima Thule at over 30,000 miles an hour, we were actually we were there and then gone. I mean, and it was interesting that it was already in the rearview mirror after the cheers died down. From the flyby, it was already gone and in the rearview mirror. Basically, and I thought that was pretty cool. It's moving. It's moving pretty fast. Moving quite fast. So I don't know. I just I really like I like the concept of Ultima Thule and what we did there, and because it was sort of a happenstance. I mean, we didn't plan to launch New Horizons so that it would intercept Pluto and then Ultima Thule. It just happened to be. Actually, when we launched New Horizons, Ultima Thule hadn't even been found yet, which I think is even more miraculous, don't you think?
it's very cool.
Yeah. I'm heading over to the Pleiades at the moment. We're just going to take a ride over there. There they are. Look at them come right in. Look at that. Isn't that nice? This star right here, this is Alcyone, okay? That's the bright star, and then you see this, it looks like a little dipper, okay? And then it's a little handle back there, Kind of an interesting collection of stars, but what I like about the Pleiades, okay, is that, for their distance from us, which I can show you immediately, if we look here just real quick, all right, you can see that the Pleiades are about 400 light years away overall. And some of these stars are closer to us, some are farther away. This one's 383 light years. Okay, let me just close in so we can see it. Okay, here's Electra. Electra is 404 light years. Where am I seeing that? I'm seeing it over here. Okay. By the way, you'll notice these numbers are dynamically updating. That's because we are in real time. So this is a real-time operation here. This is Merope, and Merope has this beautiful combed nebula that you can see some of it in this picture, which isn't actually very high res. And I didn't take this picture, obviously. But Merope's 380 light years away. And Alcyone, the one I just pointed out to you, is 403 light years away. All right. Then we have Maya, and Maya has a little nebula around it, which I've shown you. We'll show you again. And this is 383 light years away. And Taygeta is this guy out here. And Taygeta is a star that's 409 light years away. And then Atlas way out here. Okay. Now, I'll tell you something interesting about Pleione here in a minute. But Atlas is actually 382 light years away. So they're all part of the same cluster. Pleione, on the other hand, at 381 light years away, they're all about the same distance. But guess what? Pleione is such a rapid rotator that it's actually very oblate. It's flattened on its north and south pole. And it's very, very rapidly rotating. So Pleione has really interesting dynamics going on there. We learn about these things by studying these stars. And you can do a study to show how fast the stars are rotating because you can look at their spectra. Again, the spectra from over here, Okay, and the spectra can give you information that tells you how fast the star is rotating. And because the spectral lines, the lines that appear in the spectrum will be shifted toward the blue or shifted toward the red, depending on how fast the rotation is going. There'll be a blue on one side, red on the other. And it's really fascinating science. Okay, and over here in the dome cam, you can see that we're actually looking really nice outside the dome. We're able to see through, and the shutter is we're just fine. In other words, we don't have to move the dome right now. So I think that's cool. And now what I'll do is take us back to our view here, which I think is kind of important to go to. And now what I'll do is I'm going to move us a little bit. I want to just to show you a little bit. I mean, while I'm taking advantage of the fact that we got some sky, we had clouds all. I wanted to start right at 6:30. And at 6:15 it was beautiful, or 6:10 it was beautiful. 6:15, 6:20, all of a sudden it clouded up. It's like, come on! Oh, I was so mad, and I got all mad and stomped my feet, like a little baby. And then I started to see breaks in the clouds, and we still see these breaks. I still see some breaks, right? So now let's go here. This is Merope over here, and Merope has this beautiful nebula associated with it. And to see it, we really got to go to a little bit longer. So we'll do, I don't want to do 30 seconds. I want to do 20 seconds, but I'll do it because there's no moon, I'll do it at 16,000 ISO. So here we go. We're off and running, and now we're going to image this area, but we're going to see Merope in particular, and look for this combed blue, beautiful nebula that's right here. Okay. I know that when we had Daryl on, Daryl is a wonderful friend of SkyTour LiveStream and of ours in general, and Daryl likes this combed appearance. It's really pretty, and I also find it beautiful. I can't help but see it as just this gorgeous combed look. Look at that. Here you can see it here. When I was a kid, I always wanted to get this nebula and capture these nebula around the Pleiades, and it's like, man, it's like, it's just so pretty, just so beautiful. We can actually do a little processing here if we go in now, and I'm gonna just do that right now. I'm just gonna mess around, and then I'll show it to you in a second. All right, so I'm playing with a couple of these features here, and let's yeah, there we go. So now you can actually see this combed appearance, and it's all throughout this region. Okay, the Pleiades stars are literally zipping through this dusty region of space, and that's what we're seeing here. All right, it's not that these stars were formed in the nebula with this dust. This is actually dust, little micron-sized particles of dust. Okay, actually spindles. They're kind of like spindles. And they reflect this particular blue light very, very effectively. And these are just I guess a feature, you would say, of these nebulae. Sometimes you have this dust in here, and you'll also see a little bit of the noise in here. But you know what? We can get rid of most of that, which we have, right? And if we don't get rid of noise, this would actually be a pretty ugly image. So we're doing pretty good here. This isn't bad, So, so that said, I think that it's kind of a nice way to show and give back to you guys a little bit of something here. Let's go back to this view. All right, and let's actually bring up our remote here. All right, so there we are. Now, and let's just check focus. I'm going to check the focus view right now just to make sure we have focus. And it looks like we do. We have good focus here.
We have a good question here.
All right.
And this is from our good friend D.
Hey, D.
One of the champions of the Family Feud 2018 edition.
Oh, and
gotta say.
what's your question, D?
It's a really good question, actually, and I'm surprised I didn't think of it because, well, he's a lot smarter than me. But it's a really good question.
Okay.
Does the dust ever move? Shouldn't the nebula change shape over time?
Oh yeah. As a matter of fact, the dust does move. Okay, as the stars are spewing this radiation. Okay, let's go back to that view for a second. As the stars, do spew this radiation, one of the things that is really interesting is that we will see a whole lot of changes. But the problem is, unfortunately, we're actually we're sort of stuck, and it's because we are just uh, short-lived creatures in the universe. And so we don't get to see the changes that would happen here, and it does change. All right, we would actually see this stuff modify and change. Why? Because these stars are spewing, copious amounts of ultraviolet light, powerful stellar winds, which will tend to blow dust away, tend to push dust, and so some of this is getting moved by the stars a little bit. All right, and actually. Let's go see. Let's go see here. Let me go. Let's go up here. Okay. Let's go up. Let's go back to our main view here. Grab the telescope and let's hop up north a little bit to this location. Okay, right here. Let me actually go back a little. I want to take us right here. All right. Now let's go back. Let's go now and take another 20-second photo. All right. In fact, let's actually go up a bit even more. Let's do 20,000 ISO for 20 seconds. Okay. So we'll take a 20-second photo. I mean, where else can you do 20 seconds of photos and see these things? I mean, you have to understand that you just can't do that. Usually photos of the Pleiades, if you want to do them, right, and just get a beautiful photo, you could be taking 10 sets of photos that are 20 minutes each long, or more, So that's pretty interesting. So, all right, now, okay, we're here again, and now I want you to look. You can see this interesting little nebula over here. Okay, this is the Maya Nebula, all right, and we actually see how there's a bow. There's like a bow here. There's like a little curved line. I'm not sure if astronomers have figured out whether that's actually due to Maya and its powerful stellar wind, but it very well could be. And so what we'd be witnessing here is something perhaps, say, a few hundreds of thousands to millions of years after the fact, where Maya is moving through here, all right. But we are actually witnessing changes all the time. I mean, the universe changes before us, and how do we know that? Well, we know that because of the fact that when we look at say Barnard's star, which is a very very red star, it's a red dwarf star, on our stellar classification. We have stars of different types, and they are, Amanda, go for it.
OBAFGKM.
Yes, very good.
Yay.
Yeah, and those stellar types are actually, for us, okay, the guide, okay, for us. So we look at Barnard's star, it's an M-type dwarf, but it's very close to us. It's only 6 light years away or so, all right? And the thing is, it's so small and so tiny, like M stars can be, that we can't even see it unless we use our telescope. We've looked at it. We've seen it here with SkyTour LiveStream. We cannot see it now, I don't believe. I think it's set. But you see, we have actually looked at objects before that are really quite fascinating. And when we look at the Barnard star, it actually moves through the sky. In the course of a year, you can see that it moves through the sky. And that's what's really neat. And the fact is, Barnard's star will actually move visibly. So, like, if this is Barnard's star, it's not. But if this is Barnard's star, and you see this triangle of stars here that it makes right now, if we shoot it today. If we come back 8 months later, it might be here, or a little bit less, maybe about here. Okay, you'd actually see that it moved in the sky. It's very rare to see a star move in the sky. It's actually something that we don't see very much of. Yet we see it every day, and we don't even pay attention to it, and that's our sun. The sun is moving against the stars because of the relative motion of the Earth going around the sun. All right? So the sun appears to move against the stars as Earth goes around the sun. Yet no one even thinks about that. But we're watching a star move across space every single day. And it's our own sun, and it's moving quite a lot. Actually, it's moving the most of anything we've ever seen because it's right next to us. You see what I mean? So, as far as, and going back to Dee's question, just finish up with that. Because the universe has large objects and the time scales are so long, because of that, we don't actually have a long enough life to see the changes. We just don't have that ability, Dee. So if we become spacefarers and learn to, I guess, get rid of our bodies and have the ability to just do any number of, interesting things that can take us, say, perhaps 1 million years and we might not even notice, then perhaps we'll be able to actually go off and do exactly that, see things change over the course of time. Large nebulae, for instance, the Orion Nebula is changing all the time. All right, but we don't see those changes because it's 30 light years across. And so the changes are at a scale that we can't see as human beings because we're not there, we're not close enough. We only see it from 1,300 light years away. And that means that over time, for the most part, it will appear over a course of, say, 100 years, the lifespan of a human at the most. It will remain exactly the same. Yet it's changing all the time on the scale of the universe. So it's pretty interesting.
Tana had a question.
Okay.
That's a good question.
Awesome.
Okay. How many asteroid fields are in our solar system? She knows there are several.
Well, actually, you know what? We have all classically been brought up to know that we have one asteroid belt in our solar system. But guess what? We actually have this Kuiper belt. And Kuiper is spelled, as you know now, I always spell it Kuiper. The Kuiper belt is a location beyond the planet Neptune, so beyond 30 astronomical units, and an astronomical unit is 93 million miles. So beyond Neptune is where the Kuiper belt starts. Pluto is technically a Kuiper belt object of sorts, and Ultima Thule, that New Horizons just passed, is something in the Kuiper belt, and we passed that. So the Kuiper belt is a belt, as opposed to a sphere around the solar system, that contains these icy bodies. And then beyond the Kuiper belt, we have the Oort cloud, and that's O-O-R-T. That's how you spell Oort. And the Oort cloud is also icy bodies, and we have found that the Oort cloud, which is a sphere of basically cometary-type objects around our solar system, actually is a belt as well. It is both. It's a sphere of objects, and it's also a established belt of objects beyond the Kuiper belt. So technically, I guess we kind of have 3 belts of sorts here. We have more than 3 belts worth of, or I should say, more than 3 kinds of asteroids, okay? We have asteroids named for their locations. We have the Trojan asteroids, the Apollo asteroids. We have these Earth crossers, okay, that cross our orbit. And our asteroid belt has a number of different types of asteroids in it, both from composition and named differences. And I think that when we look at objects like that, and we look at, say, the Kuiper belt objects in particular, we're looking at changes in composition that go from rocky, like our asteroid belt, okay, out to icy, right? And then from icy, where does it go? Well, more icy, okay? The farther you get from a star, the more deep freeze you're in. You know what I mean? And that's something that I think is very important to understand. So that said, I think that we're actually, by reaching where we have with the Kuiper belt object Ultima Thule, we've actually made some really important strides, and I'm really happy to see that this New Horizons probe was giving all greens on its checkup, basically, because they didn't know whether it survived the encounter. Now, what do I mean by that? Well, we didn't know whether Ultima Thule had other things orbiting it, and maybe New Horizons could have slammed into it. And so when they were checking on on the location of New Horizons, they actually were waiting for telemetry coming in saying that the probe still was with us. And when they got that first indication, there was a lot of hooting and hollering at JPL, Jet Propulsion Lab. And then one by one, the different mission directors gave Mom, the mission operations manager, they gave her the green lights on the different subsystems within the New Horizons probe. And that just was amazing to hear all that. And boy, I tell you, it was tense. It was tense, you know. But so that's sort of long-winded, I guess. But that's kind of hopefully that answered the question. Anyway.
We have someone here, Electric, the Aliens Universe channel.
Okay.
Saying, Tibber from MUFON Global here.
Oh, yeah, I know.
Gonna send a link to MG. Do you know who that is?
I know Tibor.
Okay. Just passing along a message.
All right.
He or she is sending a link to MG.
Okay.
So, there you go. There's your message. And Flashback wanted any word on imaging from the probe, and we discussed that. It's going to take a long while.
Well, it's going to take 6 hours for data to come down when they start sending it. But keep in mind, if they send something, the way these probes work is they don't have backups. So if they send something, they have to really make sure they're going to get it. Okay? If something happens to the data where the probe has a fault and that piece of data doesn't get out of the probe, or it gets out of the probe in a corrupted manner, it's gone. You know, these aren't like big hard drive computers where you can just go get your backup, you know. So they have to really be careful and be sure that all systems are working, all data retrieval facilities, all downlink stations are in range before they actually start sending that photo data. The most critical science data has to be sent when everything is absolutely perfect. And that's the problem. We have to make sure it's going to be perfect. If it's not perfect, well, then we're going to be stuck. Out of luck. Let's get a spectrum of the Pleiades.
I wanted to know, is the Oort cloud considered the end of our solar system? Is that kind of what embodies it?
Yeah, sort of. But the Oort cloud, here's the thing. Okay, the current thinking is that our solar system technically extends 3/4 of the way to Alpha Centauri. See, 3/4 of the way to Alpha Centauri. That's huge. That's a very, very large distance. But the influence of the sun, when I say that, I mean the outer objects in the Oort cloud are still gravitationally bound to the sun, like that far out. However, the fact is, where the sun's influence ends in terms of the solar wind being somewhat indetectable from the rest of the interstellar medium. That's called the heliopause. And that's the location that Voyager 1 went through, and Voyager 2's gone through too now. Very cool.
What's the distance between Ultima Thule and the edge of the Oort cloud? The inner edge of the Oort cloud?
Not sure.
Like, is that where it's heading? Like, it's just kind of going to wherever?
Yeah, it's actually, it's actually going to... it's going to get to wherever. It's actually going to get to. I don't know how far it's going to go before it actually has to, give up the ghost. Basically, I don't know how long its energy is going to last, but definitely is going to last a while. But I don't know how far it's going to go before we. I don't know. Actually, I don't know how far to the heliopause from where it is, technically.
Well, even if it keeps going and it runs out of fuel, it dies, it just stops working.
It's not going to stop moving.
Well, that's where I was going. Yeah, it's just going to keep...
Oh, yeah. It's going to keep going.
Going.
By the way, just...
To where? To, like, right through the Oort cloud and who knows, and beyond?
Yeah, exactly. That's right.
Right out, eventually, to, like, the cosmic microwave background?
Well, that's really far away. But...
like what would stop it other than hitting something? Like could there be more Lagrange points out way past the Oort cloud?
No, that wouldn't be that.
No, because it uses the sun.
Yeah, the influence of the sun is too small, and it's moving too fast to be able to just stop somewhere.
What about?
It can't park in space because it's going way too fast. Yeah, but still, that's not it's not a bad thought. I mean, there's some really interesting stuff there that to be digested by people trying to wonder what's going to happen to the New Horizons probe eventually.
Like, I mean, if it went out to Alpha Centauri, couldn't it use that star and those planets, exoplanets, to create a Lagrange point?
It's moving too fast, though. See, that's the problem. It's moving too fast.
If it had solar panels on it, could it have slowed itself down using their star?
No, it would have to use some type of fuel, or it would have to use the gravity of another planet that it goes by or near. So that's the thing that is missing here. We don't have any knowledge of any planet out there that it could actually go tooling through, or go tooling by to actually give it, some kind of a boost. But in other words, stop it. We don't know how that. There's nothing to stop it. By the way, I just want to mention, okay, what you're seeing here on the screen. This is a spectrum of the Pleiades. I've broken the light from the Pleiades. You can see them down here. I've broken that light up with instrument number 2 right now. Instrument number 1 is still sitting here dutifully looking at the Pleiades, but on instrument 2, I've actually got a spectrum here that I created of the Pleiades, and I let it drift, which is what you see here. It's a little off perpendicular, but don't worry, I can fix that. And when we get in close here, you can actually see something really interesting. All right, as we look at these spectra, you notice even when we get to like this guy, what do you see missing from this spectrum? Okay, what's missing here?
Red?
Yeah. We don't see a whole lot of red. Why is that? Well, when we look at the Pleiades stars, and again, these are drawn out because I let them do this to widen our spectrum. These stars are hot blue stars, so they don't have a whole large red component, but they do have red component, as you can see right here, but it's not really very obvious, okay? And then you also see something else. When you look at it, you can actually see that there's some dark lines going through. Okay, you see dark lines crossing down, going down through the width here of these. And these are what are called absorption lines. They're lines that are created by the absorption of by outer atmosphere of these stars, of very hot energy coming through from the interior of the star, and they absorb a little of the energy at certain wavelengths, and that's what we see. Those certain wavelengths are the signatures of chemistry, like this line right there, okay, and this line right there, and here. These are all the signatures of a particular type of chemistry going on inside the star. And later, in another stream, I actually have another system. I've got more broadcast systems set aside here. And this broadcast system is going to allow us to see dynamically. We'll be able to actually analyze this spectrum of the star directly, and then watch what happens when we actually get when we actually take the spectrum into this particular program and analyze the spectrum. We'll be able to see what is in the star by bringing up samples and so forth to look what it's got. So there it is. That's spectral stuff. I wanted to do a little bit of that with you tonight, but not necessarily all I need to do. I wanted to actually do some of it just for fun. But let's go back now to our view here. Actually, let's go to our planetarium view. All right, so we just looked at the Pleiades there. We saw some beautiful reflection nebulae. And now let's go back down and let's see. Let's look at where Orion is aligned. You see how it's aligned right here. It's not quite to the southern. The south is directly here. I can see that. If you turn off the ground, you can actually see what's below the horizon. Okay. And we don't get to see those stars from up here, and that's kind of sad. I really wish that we would, but we don't. So if we want to turn on our constellation lines, we actually see now this is Orion right here. Let's turn off that. Okay, and next to Orion the Hunter, all right, we have Canis Minor. This is the little dog. Okay. And you can see him there, right? And then we have...
I'm still seeing a stripe on your screen.
A stripe?
That has a bunch of numbers and percentages.
Oh, I think you're missing the whole scene. I think you're supposed to see this.
I mean, I know there's a bit of a delay, but I don't think it's supposed to be that long.
Yeah, no, I think this is what you're supposed to see.
There we go.
Yeah, okay. No worries. And
is it Sirius the dog star?
That's down here, yes. See it? And Lepus the hare. Okay. And here we have Canis Minor. This is the little dog. All right. I think that's pretty cool. I like Canis Minor. And there's the Gemini twins, Castor and Pollux.
No, not what's under them on top of the unicorn.
What, right? What?
Oh, is it a little dog?
Yeah, that's actually Procyon. That's Canis Minor.
Right, Canis Minor. Okay.
Yeah, isn't that cool?
Yeah.
Yep. And this is Monoceros here. Okay. And
that's one horned.
Yes.
Yeah.
Yep. That's exactly right. Monoceros.
Oh, sorry. Is that where you were going? Did I?
No, that's fine. You didn't do anything bad. That was fine. Okay.
Well, the few that I do know, I have to call out because there's not many. So.
No, it's okay.
I like when I recognize the star.
Sure. That's good. Now let's see.
And I know Castor and Pollux, but I don't know the other ones. Like one of their knees is Gem 6 or something.
Oh, are you talking about the star down here?
I'm talking about all the stars. One's a shoulder and one's... Okay.
This is 18 Geminorum.
Shoulders and elbows and knees and feet.
Yeah.
Okay.
Okay, yeah. These are feet here. This is Alina and Alzir, and this is these are like the feet of Pollux. Okay, then there's Lambda Geminorum here. And you talk about the shoulders. We're looking at this here. This is that's Iota Geminorum, and this is Kappa Geminorum. Okay, and then we have over here, we have Tau, I think it's Tau Geminorum. And then Castor and Pollux, of course. But see...
And every time you click on them, it's saying they're double stars.
Yeah, well, many stars are.
A lot of these double stars? That's pretty cool for the twins.
Yeah, many. Well, that's true. But then, then again, there's many double stars in the universe.
Oh.
Okay.
Yeah, but are there generally that many double stars to make up a constellation?
Yeah. It's sort of kind of on average. It's not a, it's not a really tremendously odd thing, actually. Well,
I thought that was still pretty funny.
Yeah, no, that's cool.
Double stars in the twins.
Yeah, well, for instance, let's go to Auriga. Okay, we go to Capella. Look, double star. How about Menkelinen? Let's see what Menkelinen is. Okay, it's actually an eclipsing binary system. That means it's actually got a star that's so close to it that we can't see it without with any telescope. It has to be seen with other instruments that can detect the chemical signatures of what's happening, so you can see there's another star passing in front of it, even though it's very hard to see. So that's true.
Okay.
So anyway, in all these different constellations, we actually will have different things that are happening within them. Okay, like this right here, Hamal. Hamal is, this is definitely not, a double star, all right? But, Hamal is actually just a very interesting star. It's actually a giant, okay? It's a K1 star, so it's a little orange, all right? But you'll notice that it's also, see the angle of the horizon? Okay, as we move toward the south, see what happens? So we actually see how... how this happens. We see how the telescope is on changes its angle, because it's actually pointing back toward the North Star.
What is that thing?
What, this?
No, it was to the right.
To the right.
Yeah. Okay. Stop. Go down. Stop. And again, there's a delay. Okay, where you've stopped, there's like a big snaky thing, and then something that looks like a desk.
Oh.
It's down. It's small.
This thing?
No.
This little thing down here?
No, that's like, I don't know what that is. It has a fin on its head. That thing, yeah.
Oh, okay.
What is that? I'm sure half of it's cut off because of the horizon, but...
No, actually, I don't think it is. I think that's what it is. I'm trying to remember what constellation this is.
No, not that... Yes, it looks like an old stove, Nancy. Yes, right beside the river.
Yeah, I don't... oh, man. I don't remember what this constellation is. That's embarrassing. Not really. I mean,
Is that true, Daryl, or is that a joke?
What do you say?
Fornax the furnace.
Oh, yeah. He's correct. Sorry.
Is that really?
Yeah. Thanks, Daryl.
That's what I was thinking. It looked like an old stove or something, or a desk or something.
Yeah.
Wow.
Isn't that crazy?
That's hilarious.
I know. And it's like, I didn't realize. I should have just selected one of the stars and seen. Yeah, see? Yeah, right there. Okay. Dalim Fornacis. Okay. Yeah, Fornax, the furnace.
That's hilarious.
Yeah. Yep. I didn't pick one of its main stars. I picked the other stars. I was trying to look to see if it would tell me. Because like when you like pick this star over here, say, okay, see it says Erie. Okay, this is Eridanus. All right. So this is Eridanus, obviously. And, when you have, like, for instance, this star here, if you don't know what that is, it's LEP, Lepus, the hair. Okay, so a lot of cool stuff. Now, I'm used to seeing the sky, of course, like this, but not with the big words in the sky. I just see stars. But still, it's really, it's definitely not bad. certainly isn't a bad evening tonight. It was originally, but now it's become quite nice. It's really become a much nicer night, much better. So I'm really happy about that. And so let's see. I want to take us now to my main. Let's go here. All right, and again,
You know, when people said they made up what they saw in the sky, they weren't kidding. I saw an old furnace in the sky. That's hilarious. Oh my god.
yeah, well,
That's why I thought it was a joke, because it actually looked like a furnace.
yeah, no, it wasn't a joke. I mean, you know, Fornax is the furnace, and I just couldn't remember. I mean, you know, that's a constellation that's right on my horizon, so I don't get to, you know, really pay too much attention to Fornax, which is sad, I guess, but it's sad but true. Let's go back to our wonderful stellarium scene. This is stellarium, by the way, in case you didn't notice that. This is a planetarium program that I like to use. And let's go. Okay, you'll see that toward our eastern horizon, we see Regulus. What is that? Well, Regulus is from Leo the Lion. Okay. And then we have Cancer. Okay. And we have the Gemini twins. And then we have Taurus. You'll notice what's happening here. This is the line of the zodiac. Okay. That we're seeing. So this is a line of which we have the zodiac in. Okay. So our mythology and everything that we know basically comes from the fact that we have these pictures in the sky that ancient peoples thought of and put up there, and I think that they're you know, kind of neat, but you know, you like that aspect of it more than I do. I like to just see some really cool stuff, you know. Now let's
because I cannot see. They just look like a whole bunch of field stars. Some look a little bigger and brighter, but some, I don't know.
I get it. I know what you mean.
But I'm working on Orion. I'm working on the belt and the sword.
Okay. I'm going to take us to this location.
So now,
here.
but Gemini isn't always above him.
Correct. It depends on how your what is it? How your sky, I'm sorry, it depends how your telescope's aimed. Okay, I can see that the telescope looks like it's very close to the edge of the dome, but not quite. I think we might have squeaked out here being able to use this setup. I may not have to move the dome. I want to show you something here. And I'm going to move us over a little bit. Okay. And now I can come back here. And if I go into 4K mode for a second, you can actually see how it starts to come into view. You can see this cluster showing up here. Never mind the pink amplifier noise here that you'll see. But that's the camera artifact. If we just increase the sensitivity of the camera, look at like a little glimmering jewel box. We see this starting to come out, and I'm gonna just drop it down a little bit because I want to bring it a little bit more into prominence. Okay, so I'm gonna do this and put it here. Okay, now what we're gonna do is we're gonna come out of 4K mode. We're gonna go back and take a picture now, and this is now gonna give us an image of say, okay, 20 seconds is good, but not 80,000. That's going to be a little too bright, I think, for this area. Let's do 10,000 actually. So we'll do 10,000 ISO sensitivity for 20 seconds, and we're off and running. So now let's go see what we end up finding here. Now again, keep in mind the camera is now open. And light from this star, that star, that star, they're all falling. This light's all falling on this particular, sensor in the same place. And that's the kind of thing that is how we actually get. It's how we actually get, light to accumulate and give us something to see. All right. So this is what we took a picture of. This is a beautiful little cluster in Gemini. It's known as Messier 35. All right. And Messier 35 is interesting, but there's something else going on too that I think you might like too, and that's I'm going to show you that too. If we come back in here now and we sort of zoom in here, and I want to kind of bring up a lot of the different objects that we can see.
That looked like some kind of global cluster.
It does, doesn't it? But it's not. Okay, it isn't actually.
Because you said something that I'm going to like.
Well, yeah. Okay, so...
What could it be?
Well, first of all, this cluster, Messier 35, it's called, is also known as the shoe buckle cluster, and that's because it's near the foot of one of the twins. See?
Oh, yes. I was going to say shoe buckle. That sounded so familiar.
There you go.
And I was going to guess it was one of the twins' feet.
And that's the shoe buckle. So now, but right next to that is this little guy, which is kind of interesting. This is another star cluster. And let's just take a look at that one. So we're going to head over to that one now. Okay, and we'll go back to our little view, and you'll see that we're moving a little bit. And I make sure that the dome doesn't interfere. It looks like we're okay. We're actually moving a little bit westward, and we should be okay. So let's take a look at our system. Okay, we're ready to go here. Let me just take a... actually, let me do a quick 20-second shot here and see what we get.
I don't know how to phrase this question, but Ian was just saying it would be neat to have a constellation contest and see how many different artists would re-envision the stars with their own objects. And I'm just thinking, like, because different cultures see different things in their skies and stuff and have different names for the same thing. And
yes.
With the catalogs, they have all these fancy letters and number sequences for objects. Like, who's to say all the stars in Orion all belong to Orion? Like, couldn't his belt be something on its own? Or, like, couldn't the top part of him be part of Gemini? You know what I mean? Like,
I do.
How do they... Like, what defines... what stars are in which constellations? Do you know? I don't know if that makes sense.
No, it makes sense.
I'm going?
Yeah, you're trying to. You're asking a very simple question, which is one that everyone asks at one time or another. And by the way, I went to the wrong object. I used the wrong key combination to get to the object. So we're doing the right thing now. Basically, the answer is that when we look at the sky, from antiquity, borders for these constellations were, assigned, and that's what we're seeing here. We're seeing that borders have been assigned, so you actually have like a border to a particular constellation. All right, and that's something that has moved forward through antiquity to present day. So that's how that works. Okay, 20 seconds at 10,000. Let's just do that because I think this is, it's going to show us some really interesting data. We're going to look at the M35 is now over here, and then we have this little cluster over here. That's very fascinating because it's actually a cluster that's farther away. All right, and we'll see in a minute. Okay, so this little guy, all right, is right near M35 right here, but that's actually there. You notice that it looks kind of red, right? It's actually more distant, and we're seeing it through dust and so forth. And what happens when we see something through dust? It gets reddened. The sun looks like it's red on the horizon because we're seeing it through more air. Well, when we're seeing a cluster through more dust, it gets reddened. All right, and when we looked at the M35, all right, we didn't see this reddening happening here, but we see it happening over here. Isn't that wild? So that's kind of a very interesting factoid about the reddening process and so forth. But it just means that it's also smaller, and if we take another photo of it, a little bit longer exposure at a higher ISO, the color might be a little brighter. We could just be it could be the camera sensor too that's causing this to look that way. But we do see, and it's called interstellar reddening. We do see this, and we have to calculate interstellar reddening when we're gauging distance to clusters and other things and stars. We have to calculate interstellar reddening so we know like kind of how much stuff we're looking through, because reddening helps us. It tells us some information about the stars. And this is just so you know, this little, look at this little tiny area right here. There's a star here, and then we got all these little stars right here. Just think, each of these is a star of its own. They may have planets around it. Each of these. This is just phenomenal. All these stars, they're everywhere. And sometimes you get these chance occurrences like this right here, where you see this line of stars. It's like, wow. Now, what are the chances of that? Well, the chances are pretty good in a 3D universe, because these stars may not even be in a line with each other. It's just that from our vantage point, it looks like we're seeing them through a line. So it's actually kind of cool. Really neat. I love studying clusters. I love studying these. We can figure out the distances to these clusters if we actually are of a mind to at some point, and we might do that, But I would just like to let you know that I think that we're doing pretty good tonight, considering that we had a very inauspicious start to the evening with all of the clouds that were around, and that was terrible. But we don't have them now, and that's really cool. So let's go and look at some other things here. If we back out a little bit, now just so you know, also this the way this works. Let me see if I can show this better. You see how you're kind of seeing what looks like the Milky Way there? That is the Milky Way. But it's kind of interesting because it's sort of the other side of the Milky Way. It's looking away from the center of the galaxy. When we're looking toward Orion, and then up toward Perseus, and up toward this area here. All right, this is Mirfak and Perseus. Okay, when we're looking up here, we're actually looking away from the center of our galaxy, almost directly the opposite direction, actually. And we see these stars of Orion so brightly down here. Let me just show you those again. Okay, these stars of Orion are so bright because of the fact that we're in that part of the galaxy. These stars are very bright to us because they're only a relatively short distance away in what's called the Orion Spur, which is a little kind of like a little hook, or a little segment of a spiral arm, and we're in that. Okay, and at the other end, all the way down toward, if we get rid of the ground, okay, down toward the center of our galaxy. This is really toward the center of our galaxy down here. All right, and we're actually looking toward Alpha Centauri down there, and your whole your 3D place in the universe is something that is really hard to understand, unless you actually take some time to go through it, But I'm pretty confident that you'll enjoy going through this, as we have been. Hopefully you've had a good time, because I've had a good time talking to you about it. Now, if you notice, have you had a good time?
You have that line on your screen again, though.
Oh, darn it all! What's going on here? How long has that been there?
Just a few seconds.
Oh shoot! I don't know why it's doing that. Okay. Yeah. All right. I'm gonna be. I can actually.
There we go.
Yeah, I can actually get rid of that for good. But I better not do it now. I'll have to do it after, because I don't want to mess stuff up. Okay. So, what I said was still true. We actually have, we actually have a tremendous number of objects here in the spur of Orion. We've seen these objects before, and I'd like to head off this way a little bit. And I'm not sure that we're going to be able to pull that off without having to move the telescope. I'm sorry, the dome. So we're going to have to look and see, because you see the dome is kind of near the edge over here, and if we go too far this way, we're going to end up having a little bit of a problem. So I'm going to have to see if we can get around that. But we'll try and work it out. Anybody have any questions at the moment?
Yes, actually, Laura got here a little late in the program, I think.
Okay.
She wanted to know, what do you think the New Horizons probe will find behind the sun? I didn't think it was going behind the sun.
Yeah, no, the New Horizons probe is far from the sun as any other probes other than Voyager 1 and 2 can be. But New Horizons has passed Ultima Thule, that Kuiper Belt object, and which is itself 1 billion miles beyond Pluto. So it's really out in the deep freeze of the solar system. And being that it's in that deep freeze of the solar system, I really think that the options are just, they're all over the place. The possibilities are just endless.
So what was the plan with New Horizons? Just to get to Pluto and everything else was a bonus?
Yeah, actually, that was it.
To get to Pluto.
When it was launched.
Not to Neptune, and they thought maybe we could push it to Pluto. That was always their goal?
Yeah, no, New Horizons was going to Pluto, but... Yeah, but then Ultima Thule wasn't even discovered when it went to Pluto, so...
So there could be a whole bunch of things we end up passing that we don't even know about.
Sure, and as
long as we don't crash.
Well, yeah, and what's funny is the likelihood of crashing is actually not very high. You might think, well, how could you say that when you got up to millions of objects out in the Kuiper Belt? Yeah, but they're all circling the sun at different distances from the sun, and they're all moving at their own independent rates, and they're not dense like say sand grains on a beach. Okay, they're separated by a lot of distance. So you might have a sand grain every mile. What's the likelihood you're going to hit a sand grain when they're spaced a mile apart, each one, and you go rocketing through, a beach? Well, if the beach is, say, 1,000 miles long and the sand grains are spaced a mile apart, okay, or even, say, 500 feet apart each, what are the chances you might hit a sand grain? Probably very, very little. So there's no guarantee we're going to survive, but there's also no great likelihood we're going to be destroyed. And we've played that thing. Think about this. Cassini went through Saturn's rings. And when we look at Saturn in the telescope, we're seeing Saturn, the rings look like they're solid, but they're not. Just like a cloud, like I showed you before. As you get closer, it's fuzzier, and then finally you're in it, and you don't even realize you're in it. Well, that sharp border is an illusion because of the way or the distance you are. So the rings look solid, but they're not. They're actually very small ice particles, but they're not like so dense that you would, like, if you brush them with your hand, you'll hit 100 of them. You could probably go through Saturn's rings and never hit ice particles and go through back and forth, up and down through the rings, for a long time and maybe months and never hit anything. You could hit something the very first time, or you could hit or never hit something. So so the density of stuff, and like the density in a nebula of stuff in a nebula, that's another thing too. There's only a few atoms per cubic centimeter, not hundreds of millions or billions of atoms per cubic centimeter like with matter here on the Earth. Okay, out there in space, there's only a few atoms per cubic centimeter. But at the great distances that we are away from these objects, the overall effect is to actually have what looks like a solid object from a distance, like the Orion Nebula. The Orion Nebula is just stunning. Okay, however, the Orion Nebula is also a place where objects are very, very sparse. There's not a lot of density there. And that's the thing that we have to understand. And that's something that I think is probably that something we'll probably explore at some point. We're going to go through looking at that. Okay, so we're fine with the dome right now. Moving to the next object here. Did that answer Laura's question to her satisfaction?
Yep, I hope so.
Oh, she'll tell you. I'll do 20
Yeah,
seconds.
because she had said she watched a NASA video today that said that they'd be behind the sun, so she was curious. But then Daryl suggested that maybe it's because Ultima Thule.
Just Thule.
Yeah, Thule. And New Horizons are in Sagittarius, which will be going behind the sun soon.
Correct. So
that might be maybe
what
she
means
was thinking.
that they're in the daytime sky.
Yeah.
Is really what that means. Yeah. That's all that means.
Yeah.
Yeah, but that's okay.
Dan had a following question about asteroids.
Okay.
She wanted to know if asteroids and meteors have their own set of orbits like the planets do.
If asteroids and meteors have their own sets of orbits like the planets do.
Yeah.
Meteors don't, but asteroids do.
Can you explain?
Yeah, I mean, asteroids are in an established orbit, typically. Around the sun, we have a number of asteroids that we know about, obviously. And we have probably several 100,000 asteroids. And a number of these are possible threats to us. But the threat reduction is actually happening every year. They have a threat assessment, and actually they take off candidates off the list. Every year. They don't add many candidates, actually. They take off more candidates than they add by far. So once they figure out the orbits of these asteroids, they realize that, oh, nope, that's not really a threat. Nope, that's not really a threat. And it's really neat. So asteroids are in an established orbit. Meteors, on the other hand, what is a meteor, first of all? A meteor is actually the debris, the residue left over from the passage of a comet. When a comet comes through, the sun bakes stuff off the surface, and it goes off into space, and it trails behind the comet. And that stuff is dust, right? Meteoric dust or cometary dust. When we looked at Churyumov-Gerasimenko from the Rosetta mission, we noticed the surface was covered with this very fine dust particles. Well, these are the pulverized remnants of ancient impacts, both at the comet and elsewhere in the solar system, that this thing was dredging up as it passed through the solar system. And these fine particles end up entering our Earth's atmosphere if they're left behind in the comet tail after being popped off the comet through the outgassing process that occurs on a comet when it gets closer to the sun. The sun bakes the comet. Stuff inside happens, and sometimes little jets pop off the comet and blow stuff off the comet. And that's called outgassing. And sometimes these outgassing events will leave a trail of somewhat, dense dust of knots behind the comet, and we might pass through those. In which case, we will have many tens of millions of potential particles falling into our atmosphere over time as the Earth is moving through that location in space where the comet tail passed. And this would give us the meteorites that we would see in our sky, the meteors that we'd see in the sky. And so that's where meteors come from. So in a sense, they're not in a specific orbit. They're debris that are left over, and they're still moving through space, but they get absorbed and diminished by planets they run into, other comets that come through. In long term, we don't have as much dust in our solar system anymore as we used to. The dust we have left is only visible from the darkest places on Earth, and it's called the zodiacal light. And you actually see this dust in the plane of our solar system rising off the horizon and going up into the sky. And it makes this conical looking shape up from the horizon at an angle, and that's actually the plane of our solar system, and the reflection of small particles of dust in our solar system. So we do have that in our solar system, but over time it'll get diminished as it gets absorbed by other planets and other comets and so forth. You had a couple more questions, I think, that you were...
I did. A few more were coming in, actually,
Okay.
during that explanation.
Okay.
Ian, are there parts of space, like in Nebula, that are really hot over large distances, meaning hot in our terms and not from the normal temperatures of space?
Well, actually, for temperature to exist, you need pressure. And temperature is related to pressure, and without pressure, then temperature isn't defined. But never mind that kind of gobbledygook double talk sounding thing. I know what you mean, and really what's going on is, if you look in a nebula and you look at the hot stars that are in the middle of a nebula, the stars are certainly hot. The stars can be 30,000 degrees, 30,000 Kelvin in temperature, and or more, and they have a high ultraviolet output, and that ultraviolet energy is what is absorbed by the atoms in the gas that are in this nebula. So, and that gas is usually hydrogen. So when it absorbs that energy coming from these hot stars, then the electrons in the atoms ionize. They leave the atoms for a period of time, and when they come back, they give off that light I talked about earlier, the hydrogen alpha, the red light. And that is in a nebula, that is actually kind of a unique spot, because the hot stars in there are pushing out with a very powerful solar wind. They're also pushing out with a radiative energy from ultraviolet energy that they're pushing out with. That ultraviolet energy energizes the gas, makes it glow in the red region like I talked about. It causes the reflections off of little tiny particles in a nebula, and that is blue, obviously, because it's very... the high energy is high frequency is blue. Low frequency stuff is red. But that's not why hydrogen glows. Hydrogen glows for a different reason, and don't get confused with that. So the hydrogen is glowing because the ionization from high energy atomic reactions, as the high energy ultraviolet hits these atoms of hydrogen, ionizes them, and then the electrons come back down into the atom at some point, or another atom like hydrogen, and it's called recombination, and they give off light. That giving off light is what we see as the red in these nebulae, as I've said. So, in terms of, is there a hot nebula? Well, in terms of the radiation, yes. If a nebula is red, it means that the temperatures have been high enough to ionize hydrogen gas. And there's some stars that aren't hot enough to ionize the gas around them, and all we see is blue. And that blue is just a reflection nebula. Now, I think that is a good question, and this is the Hubble's Variable Nebula. This is a reflection nebula as well. The star that's causing this is not that little star you see there. It's actually a star that's buried inside a dark area here that you can't see, and it's causing this to reflect. This is dust. It's causing light to reflect off that dust from that star. But I do want to go back a bit because I do want to take you to another place where we have actually seen how stars that are not quite hot enough will cause reflection nebula and not emission nebula like in the Orion Nebula. And that location is going to be right here. I'm going to take us right to this spot because this is a perfect spot to go. So I'm going to move the telescope there, and we're going to go back to our wonderful view here and move us in. All right, and now as you see, we're kind of pulling in here, and let me just, it'll readjust. It's coming in by itself, and we'll get our controls back momentarily after it's finished. We got them back, and now we're going to move a little bit toward the west this way, and then we'll stop right about there, and we'll move a little bit down to here. This is good. Now let's go and take a photograph, because in this one photograph we're going to see everything we've just been talking about that will answer a lot of those questions that you had, and it's a really good question. So let's go up to, say, I'll say 16,000 ISO for 20 seconds. This will be a long exposure, but Orion is in a position where it's sort of in the darkest area right now of our sky here, and so we'll actually get a nice view, a really good view of it, I think. So let's go see what we get. So this nebula here that you'll see is the Running Man Nebula, and then this will be the Orion Nebula, and you're going to see them in the same photo. There we go. Look at that. Okay, now this is the Orion Nebula down here. All right, and this is an emission nebula. There's the red. This is an emission nebula right here, and then up near the top. Okay, and I'm gonna just I want to just bring us back down a little bit. I want to get this back. It's a little bit. The view is a little cut off up there, so I want to fix that. Let me just do that. Let's see. Well, we can see the blue up there, and what I'll do actually is, I'll come back to this in a second. I'm just going to go back for 1 second, and I'm going to take us back to our previous view, and I'm just going to go up a little and redo the photo. We know what the Orion Nebula looks like, but let's just go up a little bit. Oops.
Okay, I'll be back in 1 second.
Okay, I'll be here for 2.
Okay.
All right, we'll do this. There we go. Okay, let's just do another one of those, and then we'll come back. So now, if we look at this again, we come back to our image here that we're looking at. You'll see that we have this guy up here. This is a reflection nebula. These are hot stars up here. All right, but they're not hot enough to ionize the hydrogen gas that may be in this region. All right. This star is hot enough to ionize the gas, and the stars here are hot enough to do the same. Okay, so now when we look at this photo, this is the new photo we just took. Okay, when we look at this photo, we see might be getting some clouds. Actually, that might be why we're getting this whitish hue in here. So let's just hope that that's not the case. Anyway, let me go and grab a little better view of this. Let me just try to pull out a little detail here to show you where I'm going. Okay, so here we go. So now when we look here, this is that blue reflection nebula. These stars are reflecting off dust in here. Their light is reflecting off dust in here. That's happening down in the Orion Nebula too, to some extent, but it's also got the heat, the radiative energy from these stars down here that are hot enough to ionize hydrogen. These are not hot enough to ionize the hydrogen, or the clouds are just too far away for that to happen. There is a limit. Why isn't the gas out here ionized as well? Well, because obviously there's some dark clouds in here, dark stuff, sure, coming in here. But this only goes out a certain distance anyway, because the star's region of influence, where it can actually have enough radiative energy to ionize hydrogen to make this red glow, is only so big. It's not going to have that energy forever. It tapers off. In fact, it actually falls off by the square of the distance away, the energy, so it's going to fall off pretty quickly. So the Orion Nebula is just a wonderful place with all this different stuff that it shows you. This Running Man Nebula shows us some reflection nebula. There's also a Mission Nebula up here, but it's very small, okay, compared to the Orion Nebula. But we find that these locations in space are areas where we'll probably be able to learn an awful lot about star formation. And that's why the Orion Nebula here is called a stellar nursery. It's actually a place where stars are being born. And these young hot stars that are being born in there, some of these are called T-Tauri stars. T-Tauri stars are fascinating objects in and of themselves. Then we have other types of stars that give off so much energy that it's almost unbelievably dangerous how much energy they give off. They would sterilize anything for a light year all around them, because of their energy. So there's some definite pluses to being around the star that's got being around the star that's actually less hot in that realm. And I think that works for us, trust me. Just for now, let me I'm going to go back.
I'm back, by the way.
Excellent.
Just listening to the tail end of that, so.
Okay, I'm going to take a photo here with the spectral system now, and then come back. I want to see, since it's such a wide-angle shot, it's going to tell me, and it's not the Pleiades we're looking at now. We're kind of in the Orion region now. I want to see what we're looking at, if we've got clouds or something, because I did notice there was a little bit of a whitish hue to our image. So we'll see. I think we're okay.
And we actually had another question from our good friend Tom from T-Toys. He made me that UFO model.
Yeah, that's Tom.
You can actually check out that video on my channel, DannyFan1.
Yep. And
shameless plug.
You should give Tom's link out for people so they can contact him.
I will.
Okay.
Yeah. He wants to know why are there tracks like rocks rolling around on the moon?
Oh, actually, that's a very good question. See, what happens on the moon is that we don't have we don't have same kind of dynamic place like the Earth, okay? But we do have on the moon we do have the fact that there are these large craters, and the craters sometimes have these big boulders that were thrown out of them, thrown up around the rim, sometimes not fully out of the crater, sometimes in the crater, and then there's other impacts that occur all over the moon, and what happens is sometimes the rocks roll downhill because they're just sort of teetering on the edge. There's lots of boulder tracks that you can see in craters all over the place on the moon. And, just because the moon is billions of years old and airless, okay, it doesn't mean that the moon doesn't have anything happening. The moon is dynamic in its own way. So we see that on the moon, and we see that the moon has actually got an entire set of things that happen on it that we might not normally, see. So I think that the moon is very the moon is an amazing place. If you guys get a chance to. I wasn't going to say go to the moon, but if you guys get a chance to look up the Lunar Reconnaissance Orbiter Quick Map browser, you can go explore. Keep in mind that I actually showed this Lunar Reconnaissance Orbiter browser several times now, actually, and it was really something. And I know that I think you were there with us at one point, Amanda. Weren't you in that stream?
Which one?
The Lunar Reconnaissance Orbiter stream?
That may... I may have been for one. Did you do a few of them? Because I think there was one I missed.
Well, there was one that got me kicked off of YouTube, apparently, if you remember that one.
I remember that one.
Yeah, so do I.
Alien remains on the moon?
No, I basically was saying that it was like... I was saying, you know, humans still remain on the moon, you know, and that's exactly true, you know. We actually had some kind of, you know, we had human remains, that's to say, the remains of humans, human endeavor on the moon is what I was trying to say at that point. And it got all muddled when I did it, and I wasn't even intending to, you know, put it up there. But I was just trying to actually do a quick copy of a stream locally. I didn't even want to put it up there, but it went up anyway, and I got booted from YouTube for violating...
3 months, wasn't it?
Yeah, for violating something, which was really silly because I didn't do a darn thing.
Then you look at some of the clickbait titles out there and you wonder...
Yeah, like, why me?
Or even some of the content, it's like, seriously?
Yeah, why did that happen
Hacks
to me?
are us.
You know? Yep, that's true. I'm going to try to go to this guy right now. This is another one that's really fun. We've seen the double cluster before, but this is a different one. And I'm going to see if we can actually get to this one. I'm going to select that cluster and then go there. And let's see if we can witness this occur. So here we go. You can see the dome moving slightly as the telescope is winging its way around. And it might... I got to get that restored for a second. It's coming back. See, it says, please wait. That's just...
yeah, I was just about to say the request was timed out or something.
Yeah, we're okay now. All right. Let's go and see that spectral shot we took earlier, by the way. I forgot to go back and check it out. Oh, no, I didn't. I had done so. But what's interesting is when we look at these objects in the spectral world, okay, you can see some really interesting data in the spectrum. And that's, like I said, we're going to check that out at some point as well. This right here, this is the Orion Nebula's spectrum. And it's just out of the shot. And unfortunately... I've got, I actually have the zoom level on the camera just a little too high. If I make it a little smaller, then we would have seen that the Orion Nebula actually has emission lines in it. We'd actually see bright emission lines as opposed to dark areas of absorption lines. And emission nebulae are called that because they have emitting lines that they're emitting from this interaction that we've talked about with the ionization and so forth. So let's photograph this guy. This should be what's called the poor man's double cluster. All right, and we'll do 20 seconds at 16,000. So off we go. Off you go. Good news, everyone. What's that from? Anyone? Anyone watching? It's from a TV show. An animated TV show. Wow, there you go. Look at that. So this is a beautiful little cluster. And I can just take off the processing, kind of show you. Here's how the camera caught it. All right. That's neat. And
12 feet tall guesses Batman.
No. But
D. Smith guesses Yogi.
no. Hey, Rocky. No. Hey, Boo Boo. How about gonna play with the picnic basket? Okay,
Is it Rocky and Bullwinkle?
Hey, Rocky, watch me pull a rabbit out of my hat. Nothing up a sleeve. Presto. Brr. Ooh, must have had the wrong hat. Remember that? It was like this lion comes out of the hat. Yeah, no,
So
it
it was
wasn't.
Rocky and Bullwinkle?
No, it wasn't.
Oh,
No.
Ian guesses Futurama.
Yes, Ian's right.
Of course it is. It's
Da,
always
da, da,
Futurama.
da, 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 da. Yep, that's right. Remember with Leela and the professor? What's that guy, the old guy? He's the one that says, "Good news, everyone." Yeah, exactly. Really cool.
Ah.
Yeah, this is cool. So this is a beautiful little cluster. I adjusted the telescope too to get some of the parameters a little better. I had some issues with the mirrors, and I've solved them pretty well. I kind of stuck around in the cold out there to try and take care of it, and I got it done. So let's see now. There's a couple other things I want to show you, and I think I may have to go and alter the dome location because I want to do this. I want to take us to. I want to take us out of here. I want to take us actually toward the north, which is up here. And I'm not sure. There's Polaris, that's the northern star. How do we know? Well, we can just do this, and you can see the northern star. That's the hypothetical, area right there. That's the center of the top of our sphere. But you'll notice Polaris isn't right on that edge. Polaris is a little farther away. And then you say, well, wait, how far away is Polaris? Well, we have a way to find that now. We just take our little angle tool, and we can just say, well, how far is Polaris from the pole? And you can see that Polaris is, oops, I messed it up. I apologize. Let me just do it again. You can see that Polaris is, where's the marking? Where'd it
And 12 Feet Tall wants to know how expensive
39.
is this program? Stellarium is free, isn't it?
It is absolutely free. That's right. Everything you're seeing is a freebie. Okay, well,
This is Stellarium.
Yeah, this is Stellarium, and I should say actually, everything you're seeing that I'm doing right now is a freebie, but the fact that what I'm doing is actually something that's quite it really is sort of expensive what I'm doing around here. But this is not, it's not meant to say that no one else can do it. Of course you can, but it's just that you're gonna be spending a lot of time. Oh, look at this! See that? Cat's Eye Nebula. I know that you're a fan of the cat's eye, but it's kind of low right now.
Well, let's see what we can do.
Well, I gotta move us around. Yeah, so I'm gonna have to go move the dome.
Okay, don't worry about it then.
Oh no, I'm gonna move the dome because I want to take us to this part of the sky now. There's a lot of stuff here to see. All right.
Okay.
So you hold everybody's rapt attention, and I shall return.
Oh my gosh.
Oh my God. I'll be back.
Okay, and while Mark goes, I hope everyone had a nice New Year's and is looking forward to 2019. So far, I know the new year is bringing us a second hour for SkyTour Radio. For those that didn't know, Mark and I have a show on kgraradio.com. That's kgraradio.com. I'll throw the link in a second. It's Sunday nights. It will now be starting at 8 p.m. Eastern. 8 p.m. Eastern. We'll be going for 2 hours. So hopefully that means at one point, I don't know when it's coming, we will hopefully have a line set up for calls. I don't know when that's coming into play as of yet. Hopefully we may be able to get guests on soon. 1 hour just wasn't enough time for a guest to come on and join us, really. So, yeah. Commander Cobra, who was on before us, he's still going to stay at 2 hours, but he's going to be moving an hour forward as well. So tune in an hour early Sunday nights on kgraradio.com. what about where you are? I'm in Canada. I'm in Nova Scotia. Mark is in Connecticut in the States. That's where this dome is. The live shots are from his front yard in Connecticut, and what we're seeing on screen right now is Stellarium. It's a free program. Hi, Fantasy. Happy New Year. I would love to get Michio Kaku. I think that would be a fantastic idea. I know people, half of them like him and half of them hate him, but I'd like to get Neil deGrasse Tyson on. I'd love to get Elon Musk on. I think he's hilarious. I'd love to chat with him. Yeah, any other people you guys can think of that you would like to suggest as a guest, let us know. We actually do have an email address. It's skytourradio@kgraradio.com. So you can email us there for, you know, any topics you might want us to cover, any guests you might like us to go after. Oh, I hear movement. Sorry, I'm not 100%, guys. I wasn't feeling the best last night as I was falling asleep, and I woke up with a bit of a cold, so you'll have to excuse my voice, and I'm just hanging in here. Oh, here we go. And Mark's back.
Like my hat?
Oh, I can only see a little bit of it now. Hold on. Delay on YouTube.
Whoop.
Come close into the camera. Oh, there we go.
I'll show you.
Is it a toque that says NASA?
No, not at all.
I have a toque that says NASA.
And for those who don't know,
I thought we were going to be twinsies.
Toques are hats. Knit hats.
Is that oh, it's an alien. Cute.
Yes. Okay, I think that we should be in a good position now to actually go to where I'd like to go. So I'm going to go try this right now. We're moving now. What the heck happened there? Okay, hang on. Let me get us. Okay, there we go. So now let's do this. Let's go move. Move us. Okay, here we go. Where is it? Sorry, just moving something. Hold on. Okay, now we should be able to see movement. Let's see where we're going here. Let's get this going. Oops, that's no good. All right, here we go. See, now we got the dome coming around. Yeah, there we go. And by the way, just so people understand, I'm actually working feverishly to actually create a dome movement software that's going to move the dome and keep the opening of the dome that you see on the screen now always in the view. That's kind of an important feature. I think I just missed. I'm going to have to go back out because I think I missed the I think I missed the dome. I think I missed clearance by just a little bit. You can see it on the screen here. You can see that I actually have an issue here. See that? You see that, Amanda?
Yes, I see that. Sorry, I was on mute coughing.
Okay. Yeah, this edge of the dome here, I'm not quite there. So I can try real quick to just take a picture, see if what I want to see is visible. I don't think it is, but I'm going to do it anyway. I'm off. And we'll see some artifacts probably in the star images that indicate we're on a hard edge, namely the edge of the dome. Yep. But I should have the I've got actually all the motors and stuff here, and I'm working on making a track to interface with a gear that I'm growing. Yeah, see, we're seeing this white area. It's white because of the fact that it's hitting the dome, and there's some stray light inside the dome. All right, I'll be right back. I'm going to do a movement again with the dome. I'll be right back.
Oh wow, guys, I got nothing. I thought I was safe when he came back. I'm like, yes, I made it. He's not gonna be gone long. Yeah, I was going back in chat. Sometimes when I have to talk, I stop reading chat, so I had to go back and scroll. Someone was asking me what the weather was like here. It's cold. We had a storm all day. My mom was supposed to go to work tonight, and she actually couldn't get in. That's how bad the storm was. They couldn't pass on a bridge down the street for me. So that's how my New Year's is going so far. I hope everyone was safe and happy and rang in the new year in style last night. I took over Ronald's radio station, Let's Hear It Radio, in chat, and played some kind of upbeat, dancey music to ring in the new year. I'm an hour ahead of Mark. I'm in Atlantic time. He's in Eastern, so it's 20 after 11 here. I think some of the snow's turned to rain, so I think it's just going to be slush. As long as it doesn't freeze up and I'll turn to ice. You're supposed to go out for a New Year's dinner tonight, but that was obviously called off. I don't know what to
Okay.
do, guys. I hear Mark, thank God.
Oh my, what were you worried about?
Hi.
You have a problem? Was there a problem?
No, I was just running out of things to say.
Oh, nonsense. See how much brighter the stars are now? I did notice I've got some icing around the core part of the telescope. I'm still stress testing it for dew, and I've purposely left off the dew cover. That the strap that you see in the image here. It's that light gray thing, going around the end of the telescope there. That's still there, but I have left the telescope open to the elements just so I could see how effective this was. It's been effective all night, and only the very central part has a little bit of icing on it. So we'll see. If I put the dew cap on it, it would have kept it from covering the telescope at all. But I just have been stress testing this. Okay, yeah, this is beautiful. Look at that! Wow. Yeah, this is what we're taking a photograph of right here. Let's actually close in on that a little bit. Okay, now to do that though, I see I'll be modifying some of this. Actually, I can tell you. I'll do this, and then zoom in a little bit, and then and now I can just move over.
D. Smith has an interesting question, but I'm not exactly sure what she means.
Okay.
She says, Mark, since you are a believer, where do you think is the most likely origin? Hypothetically, of course. I don't know what that means, a believer in UFOs?
Well, UFOs to me are just, spacecraft from another civilization. Maybe
Can you
that's...
clarify that, D? Is that what you mean? The most likely origin of what? Because he's a believer.
I could just say from a point of view of,
that could be like evolution, like humans. That could be aliens. That could be anything, So I just was hoping for clarification.
Well, you shall get it, I'm sure.
Yeah.
Meanwhile, I'm just gonna.
Some people are saying.
What?
Hi, Ben. Happy New Year. Some people are saying other life, origin of human life. I'm just waiting to see what she has to say.
Okay.
Yeah.
All right. Go a little more. There we go.
That's got people thinking.
Sure. I think that's great.
Cosmic visitors is what she says.
Oh. I have plenty to say on that.
I'm sure you do.
I do. Well, the thing is, I think that, and it's not like a cult thing where he's a believer, like that kind of thing. The truth of the matter is, when we talk about cosmic visitors or, visitors from another world, really, that's, to me, again, just the fact that civilization elsewhere managed to develop the technology to go interstellar. If you want to think about it, we're doing it now. We're doing this now. I'm not talking about New Horizons and Voyager 1 and Voyager 2 leaving the solar system. No. That's primitive stuff. I'm talking about NASA funding a lab to pursue the Alcubierre drive, which is, the drive that will warp space and allow you to compress the distance from your originating location to your destination and lengthen the distance from yourself and your original or your originating point. In other words, it's like folding space to bring your distant destination closer to you while making your current location farther away. Like Earth in Earth orbit. So the Earth would be much farther away. And that folding process is what the Alcubierre drive does. That's something that NASA's actually funded a lab to study. And the reason they funded it is because of the fact that the energy requirements to create basically what's called the warp bubble that surrounds the ship that was designed originally by Miguel Alcubierre has been refined so that it no longer needs the same amount of energy. It needs literally 10 to the 26 power less energy than it used to. And the reason is because Harold White, a physicist down at NASA, redesigned the Alcubierre warp bubble generating mechanism and found that he could reduce the amount of power required by that amount. So now we are looking at a potential funded, program to create an Alcubierre drive. That's really cool. Yep. We're actually this is something called the Iris Nebula. The Iris Nebula is really not Irish, but the Iris Nebula. It's really pretty, and it's there's a little bit of a processed view of it. This is a reflection nebula, and this star is reflecting. It's hot, yes, but this star there's a lot of dust around this star, and we're actually seeing the dust. Now, the view is not as good as it can be because the sky is not as perfect as it could be out there, but we're actually seeing a pretty good view for what it could actually be. It could be a lot worse than this. But we're doing okay. This is not bad. So now, if I want to take us back to just the view, this is the raw view out of the camera, and with a little processing, it looks like this. All right, so it helps us see it a little better. So now let's see if we go back and go to our main view here. You have a question again?
I do.
Okay.
I'm dropping them into Skype so I don't lose them as the conversation scrolls.
Yeah, thank you.
Kimbo2 had a question.
Okay.
And it's in regards to that hole that they found in the ISS. It was made by a drill, and they patched it up.
Yeah, it was actually in the Soyuz spacecraft, actually.
So yes, that's right. Kimbo wants to know, at what point would a hole have been too big to patch?
Ah, well, it's a good question. I don't.
Very good question.
I don't.
It's a scary question.
Yeah, I don't know the specifics to actually say how big the hole would have to be before you could patch it. But I do know that the hole would actually be. Well, it's going to be a little bit larger than what they did patch. Here's the thing, though. That what happened, it said it was made by a drill. Yeah, it was. But the thing was, I'm not convinced at all that it was done maliciously. I think it was an oversight, an accident. They noticed the drop in pressure, and they discovered that there was this hole in one of the casings in the Soyuz.
I thought that they inevitably came to the conclusion that someone accidentally drilled while the pieces were still on the ground on Earth in a factory.
Well, it was actually, I think, it happened, I think, on the Earth, as far as I know. I remember reading about a whole bunch of stuff in the story because, clearly when you started thinking, oh no, was there sabotage on the ISS? Holy cow, that's kind of a scary thought, So I wanted to, get to the answer and figure out what get me to the bottom line. What the heck happened here? And it turns out that it's probably likely that it was something that occurred on the ground, possibly after some type of repair was done. And what can I say? I don't think that somebody would intentionally try to destroy the space station. I mean that I just think it was an oversight of stupidity, frankly. Bad processes, and so I don't know what to say about that other than the guy that did that probably was a real. It was probably a really, really stupid move, bonehead move, basically. So.
Sorry, I just accidentally deleted someone's post and I hit the wrong button. I'm sorry.
Why'd you do that?
Because I'm sick and I hit the wrong button.
Oh, come on.
No, since it was a link and they were in a mod,
Right.
it said either allow or dismiss, and I was gonna show it and I accidentally hit it, so I just got it back and put it in there. So
Okay.
that link I posted, that's from Chris Elliott, guys.
Yeah. Well, that's good. Don't. Chris deserves to have his stuff seen. That's good. But glad you brought it back.
No, he's an excellent astronomer too, and do check out his channel. He does these long exposures too. Only he will do them for like 20 minutes or longer.
Yep.
He gets great pictures, but that's a lot of dedication.
You betcha.
Yeah.
You betcha. Okay, I'm gonna go to another object here. We're gonna see if we can get to a pair of galaxies that are just beautiful. All right, so let's see if we can do that. I'm gonna take us there now and see if I have to move the dome again. I won't have to move the dome once I have the my dome rotation system in place. Okay, let's see what's going on here. Okay, I see stuff zipping by. Oh yeah, clearly stuff zipping by. Go into. That's funny because I see stuff zipping by, but okay, here we go. And I'm just gonna bring us up here and see what I can get. Oh yeah, you can clearly see right there. You can clearly see it. That's the target we're looking for right there. So what I'll do is I'll actually bring that a little bit eastward. Or no. Yeah, no, I was right. Eastward. Duh. My mind is going. My mind is going, Dave. I can feel it. I can feel it. I can feel it, Dave. Name the movie.
Going with Hal.
Oh. You ruin everything.
I was right.
Yeah,
well,
you
you
were.
asked everyone. Why can't I be
did.
part of
I
everyone?
did. You're part of it. Yeah.
I can't remember. Is it?
Well, now everybody
Is
knows
it?
the answer.
Wait. Not Space Odyssey. No. What is it called? It's. Don't tell me.
All right, I won't
someone
tell
will
you.
have it in chat
Somebody
before
will
I
tell
even
you
get it.
before you know it, and they'll say you were right, and then they'll say you were wrong because you didn't say the whole name.
Well, no, I know it's the one with Hal in it, but I don't know the name of the movie.
2001: A Space Odyssey.
It's okay, a Space Odyssey. Yeah, that's right.
Well,
Just
sort of.
getting there.
2001: A Space Odyssey.
Wow.
Yep. All right. We're going to take a picture of this galaxy, and I may have to move the telescope. I'm sorry, the dome. Yeah. Because we're not... It's beautiful, but we're not... It's just gorgeous. This is called the Starburst Galaxy. M82.
12 has an interesting question.
Okay.
And I think it's going to be one of those thinking ones.
Okay.
Well, you probably have an answer, but how
Right.
fast would a bullet fly in space at the speed of light?
The speed of light. Actually, how fast would a bullet fly in space at the speed of light? Well, the speed of light's 186,282 miles per second, which is the same as going 7 times around the Earth in a second. All right. Now, aside from the fact that a solid object like a bullet can't go the speed of light without being converted to pure energy, if we the basis of the question is how fast would a bullet move if it was out in space moving at the speed of light? It would be moving at the speed of light, which is that speed I just gave you. So if it's supposed to be a trick question that, objects, mass objects of solid, a solid object can't move at the speed of light, well then, yes, that's also true. You cannot move a solid object like that at the speed of light. You can't go the speed of light without it converting itself to pure energy, in which case you would not have any object anymore. It would all be converted to energy. And that's that. So, you know what I mean?
Yeah, but
what? That's a better image processing of that galaxy, huh? That's better. That's pretty good. But what?
I don't know. What would happen? Would it just decompose because it couldn't turn to energy? Would it just
No,
vibrate the atoms to the point of just...
They would just become energy. They would not hold that particular pattern anymore. Would be gone. It would just be pure energy.
But how would a bullet turn into pure energy?
Well, because the atoms that make up the bullet would be moving faster and faster, being asked to move at ever-increasing speed, and it would end up being converted to fully energy. I mean, once you get to a certain point, the atoms...
Would that happen with any material, though?
Yes. That's the whole point. Yeah. Human beings can't travel the speed of light either. A spaceship can't travel the speed of light. A toque, your hat, can't travel the speed of light.
No, I know, but if you tried to push them to the speed of light, they would all turn into energy?
That's absolutely correct. Yep. You have spoken wisely. Name that movie. Oh, look at that. That's pretty. That's not a bad view, huh? That's a beautiful view of the M82. We should call this the exploding galaxy, but in fact, it's actually a starburst galaxy. It's actually undergoing rapid star formation. This area here, this reddish area, is actually. Let me see if I can adjust it. Was
it Indiana Jones?
Huh?
Your movie quote was in Indiana Jones? Was it The Matrix?
You have spoken wisely. Yes, it was Indiana Jones.
Oh, yay, Chris.
All right. Awesome.
Amal wants to know, can you do a stream show and show off the behind-the-scenes technologies, softwares, and whatnot? Well, it's kind of what we're doing with Stellarium right now, a little bit.
Yeah, but
I've done shows like that in the past, but yeah, we could always do another one, yeah?
I think what now Amal is asking for is, how is this all integrated together
Oh.
to show like how are we seeing image processing right now, and then I can just turn it off like right there and put it right back on. I mean, how how is it that, like, for instance, he might be wondering like how I can show, the dome cameras as well as the camera settings, and then have at my ready disposal have the ability to move the telescope here, with the dome ops here. I mean, all this stuff together with a live view. How is this all integrated? I mean, this is actually it's not. It isn't the simplest thing in the world. It's actually kind of a messy process if you don't know what you're doing. And for the longest time, I didn't know what I was doing. I had to figure this out like anybody else. But I did. I mean, it takes time. Wait until I have the dome rotation. I mean, I've got a microprocessor, which I'll show you. Okay. I have a microprocessor that I have, and I'll put it on the camera here. This is a microprocessor right here, and this microprocessor is one that's I know it's a little out of focus because I have the cameras focusing on the screens. This is going to control the dome rotation so that the opening of the dome will always face where the telescope is. And then I have motors, which I'll show you too. Okay, here's one. This is called a stepper motor. This one actually I took off my laser cutter that is obsolete. That is to say, the stepper motor is not obsolete. The laser cutter is. And so I'm going to use this motor to actually turn a gear at the top, and it's going to interface with a toothed belt around the whole perimeter of the dome. And stepper motors are interesting because they move very specific distances. Okay, they have steps. Okay, so as you turn this, you can feel each little discrete step. Click, almost like a click, 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 click. And when you can turn it by hand, but when they're powered, right, these are extremely hard to turn, and they have a lot of what's called torque, that is turning ability, and that's something that I'm going to need. And I'm going to be able to use that stepper motor to drive the dome around. All right. Then when this gets transferred to Arizona, the dome is going away, and I'm going to have a roll-off roof, a whole peaked roof which slides right off the entire square building. So you have a square building, and the dome, the peak of the roof, the whole roof is going to slide right off onto rails that go along the back side of the building. And that roll-off roof will then expose the telescope to the sky, and you'll be able to work with the telescope. Really fundamentally easier to deal with than a dome. A dome has to spin the top and open the shutter. The shutter is a mechanism that has to open to allow the telescope to look out, and then you got to keep that opening facing wherever the telescope is. A roll-off roof, you just roll the roof off. That's it. You're done. Now you go on to the next thing. Figure out the next stuff. So that's going to be what I'm going to do. So stepper motors, it may not be a stepper motor to control rolling off the roof. I have this motor over here. This is another motor. This is a very, very high torque motor. In other words, it can withstand has a lot of power and strength, and it can turn and rotate a finely balanced roof right off of a building with no problem. I have several motors of this very kind just for this purpose. So that's going to be what I'm integrating, and the whole idea is I don't want to have to ever touch the dome. Okay, I don't ever want to touch the dome. I don't ever want to have to go out in the winter, and I want to be able to have the power completely off and then turn on the power, and then the systems come up one by one. And that's not so hard. Not so hard, actually. The key item will be getting the special code to link to the observatory so that I can connect to the observatory, because it changes every time. every time you restart the computer, that code changes. And so I have to have a way of getting that code sent to me, and only me, so that nobody else can get in. Now, on top of that, think about this. I'm going to take another photo here as we're waiting anyway. I'm going to take it a little longer. I'll say 30 seconds at, it'll be a little bright, but we'll work it out. 32,000. We're going to look at that. That was the Iris Nebula that we're looking at. So when you actually go ahead and try to create an observatory that's going to do everything autonomously without any interaction from a person, it just turns it on and it knows what it's doing. The level of complexity goes up by leaps and bounds. So it's going to take quite a bit of effort to do this completely, but I'm really looking forward to the attempt. Sorry, I didn't mean the Iris Nebula. I meant M82. I apologize. This is the Starburst Galaxy as before. Duh. Sorry. Yeah. So, that said, I am thinking that. Yeah, that's pretty. That said, I think that the challenges can be overcome, and I can work out a way to do all these things. And then the idea is I'm gonna basically take SkyTour LiveStream on the road. That's what I want to do. And wherever I go, I will access the observatory and take people for nightly journeys from a place like it's in Arizona, but it'll be a place where I get 300 clear nights a day, or 300 clear nights a year. So there's only going to be 60 bad days or so, and on average, sometimes more, sometimes less. So that's kind of the goal, and I'm really looking forward to that. I know that SkyTour LiveStream is a neat a neat process that we invented. I think that's a great way to make public outreach the way to get astronomy out there. Actually, I know that people enjoy it. I know they like to see the goings on behind the scenes. I like to show you that. I'm very transparent about all this. I don't have there's nothing to hide. I really just think that it's a lot of fun, and that there's a lot of people that would really have a good time, and learning about what we're doing here, So that's kind of where I head with these things.
We have a request.
Sure.
I'm not sure if it's possible, but I'm going to ask it anyway. Cosmic Lettuce wants to know, can you get M82 and M81 in the same field of view?
Aha.
Is that possible?
Well,
and if so, could we try?
Okay, here, let's try this. Okay, I know what he's asking for. Okay.
Could be a she.
Oh, that's true. But Cosmic Lettuce.
Cosmic Lettuce is kind of gender neutral, I think.
Okay, this is the galaxy that we're looking at, and our view is kind of like this right now. So the other galaxy is right about there. So could we do this? Maybe we can. But here's how we'll do it. Let's do it by actually going back to our view here. Let's do this. All right, and now let's bring up our telescope control, and let's just take us down a little bit. Okay, that might be too much, but maybe it's not. Let's do let's just do a 15-second exposure at 32,000 to see if we've got it. We might have the Starburst Galaxy here and M81 down here. I'm predicting right about here. So I'll leave my cursor just to see if I'm that far off or not. So, well, there's M82 at the top again. And here's M81 just down here. Just off the view. This is again, like I said, if we go back and we look at the actual amount of the actual amount we have of field, it's really close. If you notice, it's really close. But we can try again. We'll go down just a little bit more. So let's go back to our marvelous little view here and take us another bit down. And I'm going to bring up our telescope control. And I'm going to set our speed to be a little bit slower. Okay, and now I'm going to drop us down. Okay, that's probably going to take M82 out of the frame. But here we go again. Let's do, I'll do 20 seconds at 32,000 anyway, just for this, just to make sure. So here we go. We're off and running. Let's see what we get. Remember, M81, which is a spiral galaxy, it was right just off the frame here, so it's probably going to be right about here right now. That's my guess. That's my guess. We'll see if I'm right. Let's see what we got. And the excitement is palpable. Oh, look, we got it. Ta-da-da. Congratulations to me. Actually, not to me. But yeah, so you can see that in our view there, we actually had it. And I don't know why we got, let's see, now I know what it was. We were looking at it from this particular, actually, was it this one or this one? Let's take a look. One of these different, yeah, see, it's just there. Okay, you know what? I'm going to do something here. I'm going to try something a little different. Here's what I'm going to do. I am going to try to bring it in and show it like it could be seen. Hold on a sec. What if I go and do this? All right, hold on. I'm just going to grab something. All right, and then do this. Oh, see, there's M80. There's M81 down here. M82 is right up here, but you just can't see it because I've got a little bit of padding going on there, and I'm going to change it. Okay, let's do this. Let's see if we can drag it in. Okay, here we go.
And this is all real-time color of the space and galaxies, right? You're not altering any...
No, I'm not.
Okay.
Okay, well, there we go. Now we have, okay, but it's still not showing yet. Let me hang on. Make it another change. Oh, that's actually gonna, oh, see, it's down here and up there. So I got the view, you see, is got to be, I have to shrink the view, but I don't want to lose too much here and make you lose too much of it. But if I just do this, maybe this will work. All right, there we go. See, now we got it. Now we have it here. There's M82 and there's M81. I'm really pushing it with my view because I've got, I've got a I've got a view here that's just a little bit less than forgiving. You know what I mean? Because I really have a marvelous telescope, but it's actually definitely is keeping us from seeing everything. But that's okay. That's just the way it goes. And then I got my processing here, so I'm going to have to change that too. Let me just change that to drag and bring this down and help us see that again. Actually, we already have it, so I just have to change the size. Let me just do this. Oh, that was a mistake. Hold on. Right, just a minute. I messed something up here. Okay, there it is. But this guy... Hang on. I'm right there with you. Don't worry, guys. I'm trying to get you to be able to see what you want to see. First things first, I got to get rid of this. There we go. Okay. Now I have the right thing selected. So now I can do this and this. And now I'm going to go back into this guy. I'm giving you what you want. Okay.
A few people are asking if you can rotate the camera.
I'd have to go out to the dome to do it, but I could, but that causes other issues too. That makes that causes a bunch of other issues. But I could. Okay, so now I'm bringing it in here, as you can see, and there'll be a point where I have to stop because I'm gonna get stuff occurring on the screen that I don't want to see. Like it's activate Windows. Well, yeah, this particular Windows, I own it, but unfortunately, it doesn't remember that I own it, and I've just been dragging my feet getting that done. But so we got this. Let's see if I bring this up here now. So that's okay.
I think Cosmic Lettuce might be a new viewer. They said in a previous live stream you mentioned that you were doing science. He wants you to elaborate on that a little.
Okay, sure.
So basically that's it's kind of what we're doing all night, breaking down stars and nebula and...
Well, a little bit, but you know what?
Figuring out distance and chemical makeup and...
Yeah, but
you
how?
Take it away.
The question is, how are we doing that? And the question is a good one. So how we're doing that is when we go over to our other view here. This is our spectral view, okay? And let me just get us to a... Okay, this is the spectral system that's on the telescope too, and right now we're actually taking this is an image from earlier where we took an image of the Orion Nebula. You can start to see the nebulas up there. If the nebula is in the middle of the picture, then the spectrum of it's going to be off, so we have to move things down and to the right to get the proper objects in the view. Like the spectrum is the golden thing. We don't care about this object here anymore. This is actually called the zero order reflection, or the zero order object. Okay, zero order means a good thing for us. That means if we have a zero order object in our view, it means we can use it as a measuring point, and all the values are zero at this point, and then we can calibrate the spectrum that we see based on that, and that's really interesting, and we'll be doing that. And so what we can do here is we can actually find out, for instance, what's going on in the Orion Nebula, what it's made of. We can find out what's in these stars, what they're composed of, what's their chemical makeup. We can see how much hydrogen is in these stars, and we can do that by analysis of the spectrum. And so that's something we're going to be doing as well. Now, as far as these galaxies, I think it would be kind of interesting to try one of these now with the galaxy. I don't know. Let's see. This is 5,010 seconds. Let me bring up my guy here. I'm going to turn off the track. All right. And after I turn off the track, I'm then going to do the exposure. Because doing this exposure with the track off gives us a broadened, wider spectrum, and that's kind of interesting. I don't know if we'll see the galaxy spectrum too clearly, but we'll try. All right, we shall try. Okay, so I can turn the track on because it's done. And what do we get? Oh, it's faint, but it's there. It's faint. Yeah, the way we get the spectrum of a galaxy is by doing something called the usage of a slit spectrograph. We're not using a slit spectrograph. We're actually using a diffraction grating, and diffraction grating is problematic at best. So slit spectrograph is coming. We got that too that we're gonna have, and that'll allow us to actually look at planetary nebulae and see these beautiful emission lines that are in these planetary nebulae as well. But so the science we're going to do has to do, first of all, in the spectral region, we're going to be looking at spectra of stars and determining what kind of stars they are based on the spectra. That's something that's well suited to doing a spectral analysis of a star. Our sun, for instance, has a lot of chemical lines in it that have nothing to do with the kind of materials that it can produce in its core. It doesn't produce. It does not produce elements beyond carbon. All right. In fact, it doesn't have that ability, but it needs to have more mass and higher temperature in the core. However, what it does do is it can create these other elements, but it was made with the other elements that it has in its atmosphere. Its outer, it's called the outer envelope of the star. So the outer envelope has, calcium, it has magnesium and potassium, and other elements in it. There's some famous calcium lines, the H and K lines of calcium. You have the Balmer series hydrogen lines. You have other lines from other, you have oxygen lines in the sun. In fact, the sun has a tremendous number of these absorption dark line features in it. And that the famous astronomer named Fraunhofer actually discovered this that our sun has this crazy spectrum in it. And so this spectrum is obviously been labeled the Fraunhofer spectrum. And the man was, quite a smart guy, a very, very smart guy. So anyway, that takes us down the path of science. We're going to go down and do some spectral analysis stuff when we get to use this product and this process. And we will do that. We will do that. So that is kind of where the science realm is going to take us, at least initially. We could also do other things. For instance, we could look at open clusters of stars, and we could figure out how far away they are based on doing a study. We can do that. We can actually figure out how far some stars are by measuring their movement against farther background stars. I know that process well because I did that. That's what I did for research. Trouble is, we would need a very accurate system to measure the position of the stars. Some stars, though, we could figure out by looking at the high rate of movement that they go through. And there are some stars that really do go through a very high rate of movement. And I mentioned one earlier, that's Barnard's star. Barnard's star does that very well. It makes a traversal across the sky. It goes like every 180 years it'll go, I forget how many degrees, but it goes, it's actually the fastest star in the sky. Relative to us, it's close to us, 6 light years. So it's actually moving at a fairly high rate relative to us. And the other thing is, we're moving too. So how do we say how fast that star is actually moving? Well, we compare the star with something that we call a local standard of rest. And basically, it's like if we weren't moving, what would the other things around us be doing? And how fast would they be moving? And that's kind of what our local standard of rest is. We assume we're not moving. We make that adjustment. And from there, we can figure out the absolute motion. So that's kind of cool. There's a lot of things we can do. We can look at the moon and we can figure out how deep the craters are by studying the shadows from data we take right here in SkyTour LiveStream. I taught people how to do that for years, and we actually ran entire programs with like 25 people in it at a time, or maybe 30 even. And we all took pictures of the moon. We examined the pictures of the moon, and we figured out how deep the craters were. We had these lunar labs that we would do with everybody to show them how to use the photograph to its ultimate potential to find all this information. And, looking at the colors of stars tells us about their temperature. And we could figure out the maximum frequency of light that a star is giving off by its color. And that's something that is very important to do. And that gives us a first step in figuring out how powerful a star is, for instance, how much ultraviolet energy it might be able to give off. So there's a real goodly amount of things that we can learn, and so I think that that's actually something that we could do as well. And so the idea is that if I want to do real science for me, well, I wouldn't be doing any of this. Okay, why is it showing daytime? Woo. Okay, I wouldn't be doing any of this stuff for. I wouldn't be doing any of this like for me for the science. If I was doing actual science, well, I might be doing something different. I might do things like try to find out if there's any stars that are moving at high speed in our neighborhood. I would do that by analyzing their light and the Doppler shifting of their spectra. Do a radial velocity study of the stars. I mean, there's a lot of different processes that we could do. In other words, to find out what's actually happening in the universe around us. And I feel like I'm kind of faltering in explaining it because there's just so much to it. There's so much we can do. I'm gonna run back out because I gotta move the dome again, and I want to be able to take us to some things around here. Okay, near Sirius. All right, Sirius is the brightest star in the northern hemisphere. All right, and you can look at Sirius and its distance of 8.6 light years, and I shall be right back. You got this, Amanda?
Oh my God. Give me something to talk about. I already plugged our second hour on KGRA and...
Yeah. Well, you can tell them what we're going to talk about this weekend. We're going to talk about Ultima Thule. We're going to talk about the Mars Insight Lander. We're also going to talk about the Mars 2020 project, which is another one, which, guess what? It's going to feature a helicopter on Mars that's going to leave the lander and fly around Mars. Not around Mars, but on Mars, in the local area around the lander. So that's another thing. I'll be right back.
Okay. He leaves me with this. Okay, that's the first time I've heard that's what we're going to be talking about on Sunday, and I don't know anything about any of those things. So we're not much further along than when he walked away. Let me see. Questions from the chat. I'll take questions from the chat. You have anything you want to ask me? I don't know anything, but you can ask me. We'll do that. What's that game? Wasn't there like a game where a group of people all saw a word and one person had the right answer and everyone else had to make up what they thought that word meant? Wasn't there a game like that where you bluff the answer? Mario asks, are the telescope controls integrated somehow with Stellarium? I don't know. I'll ask Mark when he gets back. This is going swimmingly. I will put that right in Skype so I have it. New Horizons, found by... Okay. Humans can be pretty clever, yes, some. where are you located? I am in Sydney, Nova Scotia, in Canada. Think east and north. I'm assuming the majority of people here are in the States. I know James Dugan is in Australia. My friend Ben, who's City Lights here in chat, he's in Canada as well. And Barry. There's a star called Charlie Brown's Christmas Tree. There is a Christmas tree nebula. I don't know if it's Charlie Brown's or not. The Christmas tree. Did you have a good I had a good New Year's Eve. I took over Earth Radio for 3 hours and played some dance music. And then I went to bed and I woke up with a bit of a cold. So please excuse my voice tonight.
Negative.
Oh, you're back?
No. Yes, I am.
Okay, look, on the bottom left-hand of your screen, it says Charlie Brown's Christmas Tree. Is that the Christmas tree cluster? And
no.
How did Charlie Brown get his name on that?
No, the Christmas tree cluster is called the Christmas tree cluster.
But look,
I know,
right
I see
there.
it. Yeah, I know.
Who's that? What's that?
Actually, we should be able to see it.
Charlie Brown's Christmas tree. Is it going to be like a little twig-looking thing?
That's funny.
Oh yeah, Mark the Shark's in Scotland. Sorry. Oh, everyone's. Kimbo's in California. Happy Mama's in Washington State.
Awesome.
Ben's in Ontario. Daryl's in Colorado.
Okay, here we go. We're moving now. So everybody that's listening, I mean, or watching? So we've got Colorado, we got Washington State. Those aren't meteors.
Cleveland, Ohio.
Cleveland, Ohio. Where else?
I don't know. Only so many. I didn't know it was gonna. Someone asked me where I was. I said, "Give me questions," and everyone pitied me for having a cold, so no one asked me any questions. Someone asked where I was, and then other people started offering where they were. So if you guys want to do a big shout out on where everyone's listening from, by all means. I was just saying a lot of people in chat are from the States. I know we have a few Canadians and a few Europeans, and James from Australia, and we have a few Australians come in here and there.
Nice.
Yeah. I think Amal is in India, I believe.
Is that true, Amal?
I think so. And we have Empire from, I believe he's from Iraq.
Okay.
I mean, Empire's not in chat tonight, but just someone that hangs out in this community.
Okay. That's really cool.
I love how far it stretches, and that like-minded people find this channel and find this community. I love it.
Isn't that cool?
It's interesting.
I'm very impressed.
Share.
I'm very impressed with the people that come on board to look at the wonders of the night sky. You know, you guys are great. You know, I mean, absolutely fantastic. You know, okay, let me do 20 seconds here, but I don't want to do 32,000 ASA. I want to do 20,000. Okay, here we go.
Oh, 12 feet tall is in Sweden.
Wow, very cool.
And Amal is in Mumbai, but right now is in Cork, India.
Oh, wow. Isn't it amazing how, I mean, you said it before about how varied everybody is and where they come from. It's amazing that how the internet has brought us all together in such an amazing way, you know?
Yeah, I love it. Yeah. And Skype. I mean, we can talk to people on the other side of the world, like, 15 hours apart, 13 hours apart, and, I don't know. I love it. I love this community. I love everything about it. Technology today is incredible.
It is. Absolutely
2019, baby.
Yep.
Even the progression of this stream, which has it been a year for the stream? Yeah.
Oh yeah.
It's been about a year and a half, eh?
Yeah.
Since June.
There's Charlie Brown's Christmas tree.
And just think how far this has come. Already we're showing off all this. Well, I say we. I had nothing to do with this.
Oh no.
I suggested TeamViewer. That was my contributions to this setup, but
yeah.
I mean, I love that, and that's what I always wanted. The pictures showing up behind the constellations and the lines that connect all the stars. That's what
right.
I wanted to see. We have a pointer now basic little things. You have like 3 cameras set up, you know,
Yep.
like the dome cams and stuff. I mean, this is amazing.
Yep. And this is, this is what we're talking about, being able to show this in the context in the sky. So where is this in the sky? If we back out, okay, where we just were, incidentally, when we go back to what we're looking at, which was Charlie Brown's Christmas tree, it's this right here, okay, that right there. And it shows the Charlie Brown's Christmas tree because it's sort of Spartan, right? It's not a rich tree. It's sort of like looks like a upside down Spartan tree, correct? Okay, that's the Charlie Brown's Christmas tree we're talking about, right? Now, but if we go over to our beautiful planetarium now, okay, we actually see Charlie Brown's Christmas tree, all right, as it sees it. And we come in here again, and you can see all the same stars, can't you? Really nice, it shows very well. And if you click on any of these stars, okay, some of them, like this one here, this is a magnitude 9.75 star. So it's not very obvious. It's pretty faint actually, and so the cluster is really just such a tiny little thing it's just amazing. Such an amazing little cluster. And it's tiny. You never catch it. You wouldn't be able to see it if you hunted for it. If you were told to find it, or if your life depended on it, you might not be able to find it. So I think that's actually a very interesting turn of events. It's really cool looking at the night sky like this, and looking for objects that would be just fun to watch and look at. I want to go back. I want to try to find. We looked at this the other night. Tried to anyway, and we had clouds. But I want to go to the Seagull Nebula. All right, and I just want to see if we can catch some of the nebulous colors here. It's really a really pretty place. So let's go there now, and let's see what we get. Here we go. All right. So as we're pulling in, now we got figure out what we're gonna do. We're gonna do 20 seconds at 25.6. I think that's best. And have we stopped moving? See, when we see our north, south, east, and west, okay, lit up, it means that the telescope has stopped moving. We call that slewing. All right, so the telescope has stopped slewing, and we're ready to take the picture. So let's take a picture. 20 seconds at 25,600 of the Seagull Nebula region. See if we can find it. It should be a fairly bright nebula right about here if we catch it correctly. I warn you.
And I actually had a question from when you left, and I wrote it down so I didn't forget it, and I just remembered now.
Okay.
Okay, Mario wanted to know, are the telescope controls integrated somehow with Stellarium?
There is telescope control with Stellarium and separately. I have multiple avenues going into the telescope at the same time. I have 3 separate controls actually going in. All right, and so I do have. There are multiple, yes. And Stellarium is one of them, yeah. So here's what I said to you before. Let me just point that out. Okay, over here we actually have. You can see a nebula right there. And well, you say, well, how can you see it? Well, we can actually see it a little better if we actually go to, maybe not. It's not showing as well. You can sort of see it there. You can see this little knot of nebulous detail there, and some down here. If I take, and you can see a little bright area here, and some of the, so we have a varied area here that we're seeing, and let's compare that to what we are possibly able to see in Stellarium, and let's just take a look at the Stellarium scene here. All right, basically, Well, you can see that's exactly what we saw. We saw this little knot, and we see this blue area. So we actually can see this, but it's a big object. And look at the field of view. If we were to take this picture and do it for, I don't know, maybe 25 or 30 shots, and then add them together, stack them, we would actually see something really cool here with the Seagull Nebula. But I may do that actually after I am off with you guys. I may do that. I think you would enjoy seeing the results. I know I would. So back here, if we go back to our view, all right, you can see that there is some nebulous detail here and there. It's actually quite a bit. There's actually quite a bit, and you can see that it's red throughout here. So this nebula is really all throughout here. So we probably have a good chance of capturing this. And it might, like I said, I want to do that. I'm really anxious to do that, actually. It's a good night. It is a good night for this. So let's see. Oh, if I take my telescopio and move it over just a little bit. Okay, and a little down. Just a little bit. Okay. So now I can go say to 32,000 for 20 seconds and take this picture again and then see what we get. I say see what we get because even though I kind of know what we're going to get, I say see what we get because the sky conditions are always a little wacky sometimes. You never know quite what to expect. And that's okay. So this will be coming up here momentarily. There we go. And it's looks a little bit bright right now, but if we were to take off the if we take off and add some processing, we can see that we have some more delicate nebulous details showing itself here. This actually stands a chance to become quite a nice photograph. And frankly, you might not think so when you look at this and say, well, what is that? It's just bright. Well, actually, there's an awful lot of data hidden in there, guys. Awful lot of data. You know, we're seeing it. There's a ton of data in here. You know, like this, like what's here. There's an object right here that's down here. Okay, right near these stars. You can see there's an object there, but you can't really tell too much about it. I mean, if I actually get into, if I go into the actual image processing part of this and kind of play with this a little bit more, then we might be able to see some more of it. Okay, so here now you can actually see there's more details in here than meets the eye. You know, this whole area is reddish for a reason because it's all an emission nebula. And actually, there's another word for these emission nebula. They're called diffuse nebulas because they don't have any. They're sort of diffused through space. No one particular star appears to be causing it to glow over any other star, but there are stars that are doing that. And the stars that are doing it are really sometimes the oddest little stars. For instance, this whole nebula you might assume is being powered by, say, that one star, you know, right here, for instance. But the fact is, it could be this tiny star way over here, or that tiny star there that's actually doing it. And you might say, well, how do you figure that out? Well, we figure that out from the analysis of the star's type, how powerful it is, and where it's located versus the rest of the cloud. We have to get a good feel for the spatial layout of the cloud anyway. So this is kind of cool, and you know, I said I was probably going to go 2 hours, and I've gone. Let's see, we started at what time? Was it
3.5 almost?
Yeah. See, once again, I started at 8, didn't I? My time.
Shortly after 8. Yeah.
Yeah, I think 8:06. I apologize
Hi,
for the
zombie.
delay. I apologize for the delay, guys. You know, we actually had.
Well, clouds came in. It was
Yes.
scheduled for 6:30 p.m. Eastern.
Yeah, that's right. We're gonna do a 6:30. But anyway, I do want to thank you guys for coming along. I know that I know you had fun tonight, because I know I did, and you guys are really a lot of fun. You guys are you know, marvelous. You're my joy and my enjoyment for a evening.
I thought you were gonna say pain.
No, that's you. But
funny guy. Look, he's picking on the sick girl.
Oh no! Oh, we got that little thing.
They'll
happening.
turn on you.
Oh yeah, well, they won't, because they know
I made it through. I'm
kidding.
happy. I think this was a success. I think it was worth the wait.
I'm so happy that
and a
you
nice
did.
surprise stream on the first day of this 2019.
Yeah, that's right. And thank you for making it through. I was really worried about you, because I knew that you were sick, and I didn't want you to push yourself.
I just stayed on mute for a long time, and I may have zoned in and out on a few things you were saying, but
Okay.
I'm still here. I'm still conscious.
That's good. Well, thank you.
Yeah.
And
I hate missing out on these, because there's so much to learn and so many beautiful views and just wonderful people in the chat. And I know there's others watching that aren't participating, but a happy new year to you guys too, as long as you're enjoying the show.
oh, I hope that they are. I mean, I expect that a lot of people are enjoying the show. We say show. It's actually not even a program per se. But you know what? I don't have any problems making it into a program per se, because if it's not always clear, it doesn't mean we can't stream. We always have other things we can do. You know, we can take some of the images we've taken and then, you know, take apart the images and show how, you know, a star cluster is made, show how the star cluster is influencing the area around it. So I think that there's a tremendous amount of stuff that we can still do, even if we don't have a clear night. So there's a lot left to what SkyTour LiveStream has to offer, I think, and I'm really very pleased that that you guys chose to, you know, come along for the ride, because frankly, I think that we are doing a bang-up job, and very pleased that you guys have joined me all along the way. And I would just like to just mention right now, just run down the list of all the people that are participating. I want to thank you guys.
Yay.
We have 12 Feet Tall. We have Ant-Man 2020, Cosmic Lettuce, of course, and Daryl. And we have DDB. Thank you, Dee. And we have you, of course, Amanda. We have Ronald from Earth Radio, who may very well have fallen asleep. I'm not sure if he's
here. He's here
Okay,
strong.
okay.
Oh, yeah.
Awesome. We have
never miss your
Flashback,
show.
FRG, Happy Mama, Ian McQueen. Thanks, Ian. Ian, I haven't seen you. I saw you the other day, and I'm thinking maybe you're kind of a recent joiner, and I want to thank you for coming along. And I love it. James Dugan, who's from Australia, I believe, and we have Kimbo 2. Mario Lafreniere is here, and thank you for coming along, Mario. I know that we've talked in Facebook a few times. We have Mark Rose, Maureen R., and we have Weird Guy, and we have Zombie Nomad. Well, it's so good of you guys to come along, and I think that there's more of you, but obviously not all of you are writing in the chat, so I want to thank you and all the other folks for coming along. And
Yes, Mark the Shark and City Lights, they were in there, but stopped typing. And Laura was in there.
Laura. Okay, Laura was there. That's right. And Mark the Shark. And
Outrageous
City
Toad
Lights.
is in there.
Outrageous Toad. I didn't see him in there. Is he in there?
Oh yeah, he's here.
Okay. Maybe he's not. But he's not in the participant list.
Yeah, that's the thing. You have to be typing every 15 minutes, I think.
You don't mean
Ben's still here. Chris Elliott, of course, he's still here.
You
I don't
didn't
know if
mean
he was on the list.
You didn't mean Outrageous Toad. You meant Righteous Toad.
I said Righteous Toad.
Oh, I thought you said Outrageous Toad.
Oh no.
Okay, yeah, no, I see City Lights has been in here. That's good, you guys. You guys are really cool. And there's Laura. You know, you guys are really, really good hardcore folks, let me tell you. So I'm
Can we squeeze in one little question here?
sure. I'm in.
Chris Elliott wants to know how long can you... Wait a sec. He wants to know how long you can go for an exposure with your setup. Like, could you go 5 minutes, 10?
Actually, I don't go more than 30 seconds. But
How long could you go?
Well, I could anytime. I could go any amount of time, but
Like for hours?
yeah, we used to. I mean, I used to take exposures that were, I'd take stacked exposures that were 45 minutes a piece, and I would do like 450 minutes. You know, I mean, I would do that, and I think that's, you know, at the time, the exposure was dictated by the sensitivity of the material on which you were exposing, like the film at the time. You know, so right now we have digital cameras, obviously, so now it's a very different discussion. You have a very different conversation takes place. You actually talk about making sure that you don't get you make sure that you don't do anything that's gonna overwhelm the sensor and stuff like that. And Chris asks about doing guiding. Well, yeah, I've guided for years. I've done guiding. In SkyTour LiveStream, I haven't done that, and the reason is because my outreach is very, very different. My outreach is targeted at people who want to see different objects all the time. And so, if we're not talking about a particular object in the sky and spending a lot of time on it, we might go to various objects, like various clusters and things like that. And you know, when we come back and look at the amount of objects that are simply around us and around this entire area, I mean, wow! I mean, there is so much going on here. Like if we go like back to our little wonderful view here. Okay, let's just back out a little bit from the Seagull Nebula and just look around. You know, we've got some really interesting places here. You know what we'll do? Let's just go take a look at something called Thor's helmet. Now, Thor's helmet is probably also going to look equally interesting. It'll probably be, it's actually a target I've been interested in for a while. So we'll go to Thor's helmet right now and check it out. All right, I'll show you what I mean. Okay, there's so much to see. So much to see in these different areas. So down we go to Thor's helmet. It's just going to be a little hop, skip, and a jump down below. And we're going to be, we'll be checking it out. See, here we go. We're coming in now. And it's adjusting. And our dome cam shows us that we're just fine in our shutter. Just maybe a little bit. No, I think we're okay. We're okay. All right. And so now we bring up the telescope controls. And we actually see that we are finished slewing. So now we can go and figure out our exposure. I'll do 20 seconds at 32,000. That sounds fine. So we'll do 20 seconds right now. Off we go. And the exposure's underway. So hidden amongst these seemingly faint stars is a really interesting nebula. And it's something called Thor's helmet. And there's a blue component, which is a reflection nebula. And there's a red component, which is an emission nebula. And with any luck, we'll see both components. And let's see if we can see those. Okay. Well, we kind of do, actually. Right there. It's pretty obvious, isn't it? Okay. That's pretty obvious. So what I'm going to do is I'm going to go back to our view, our live view, and I'm going to grab our telescope controls and I'm going to move us over a little bit. I'm going to move us a little bit to the west. Okay, because Thor's helmet was right about here, so I'm bringing it over a little more. Going to center it up a little bit. Okay. Okay, and now we'll do this again. All right, so here we go. Taking another picture, 20 seconds at 32,000. ISO. And this is going to show us Thor's helmet kind of right about here. And you'll see the two components. Thor's helmet is primarily, it has that nice blue cast, but it also has a red H alpha or hydrogen 2 region as well. And there it is. It's pretty darn classy, this thing. It looks nice. So if we do some processing on it, we see that it jumps right out at us. Okay. And that's kind of a little overdoing the processing, right there. And I'm going to try and bring that back just a little bit, just to kind of get us back to a semblance of a little less than this extreme here. And then you'll be able to actually see a little of the other colors in Thor's helmet. Okay, so now, yeah.
Isn't Thor's helmet a Wolf-Rayet star?
Yeah, actually, there's a whole a Wolf-Rayet star is actually a very high energy output star that causes these tremendous shock waves in the interstellar medium, and if it's caused by a Wolf-Rayet star, that's why we see it just like we do. Okay, but Thor's helmet over here, all right, you can also see there's a little red nebula here, part of it here, and I'm actually gonna make this my focus after we get off the stream. I'm gonna get a image of Thor's helmet. We're gonna keep going with Thor's helmet, I think, just to give us a nice little image to explore. So I think that'll be fun. Yeah. So as you can see, I'm pretty stoked about some of the views we're getting. This noise, you can see this noise here. Let me actually zoom in to show you. Okay, see all this noise in here? And this noise is something that can be extracted and removed. And that's what we're going to do. Okay, this is the actual size of the frame. Thor's helmet actually, well, it's actually why I show you there. I can just show you over here. Thor's helmet actually goes, it's pretty extensive. It actually goes into this area here. Okay, we saw some of this red in here. We saw a little of the red down here. And if you don't remember that, let's go take a look at it. It's right over here. And if we go ahead and take our processing and bring it in, we can see that Thor's helmet has some of the red over here, as we talked about. Okay, and it's really looking pretty nice. So, are there questions as well about that, or?
No, not really.
Okay. Well, alrighty. No worries. All right, so that is the area known as Thor's helmet. So let's go see if we can go look at another object that's right nearby here. I'm taking it and doing it because it feels like a good thing to do.
So much for saying goodnight to everyone.
Oh, I know, right? You thought you were so sure I was leaving, and then all of a sudden I'm not.
I'm never convinced you're leaving.
I know. I'm just not excited about leaving. It's such a nice night. Why would I want to do that? Why would I want to do that?
I don't know.
I know. Okay, but we are kind of low, believe it or not, which is kind of crazy. Yeah, that's amazing. We're actually so low. Look at how low we are. See how low we are?
I see it.
Wow, that's pretty low. That's low. Actually, I'm not sure. Yeah, see, that's what I thought something was off. had a little issue there. See, it was low in the southern sky, but not on that steep of an angle. That was a weird thing. Okay, but while we're here, there's Sirius. Let's go. Let's see if we can look at. Well, we can check out the little beehive. We might as well do that while we're here. And I'll drive us over there. So now the telescope's heading over there. And while it's heading over there, we'll look for some other things that we might want to check out. Okay, but meanwhile, the actual little beehive is this little cluster right here. Let's bring up our telescope controls and move that a little bit westward. Okay, a lot of twinkling because it's low in the sky. And let's do not 32,000. Let's just actually drop it to, say, 12.8 is fine, and we'll do it for 15 seconds. All right, and then we'll get to see the little beehive. Okay, so let's get this to come back in. Here it comes. Wham bam, there we go. Here's a little beehive. It looks really nice. If we want to hit it with a tad of processing, then you get this. Okay. I mean, notice it made a huge difference, right? I mean, now we're also getting this rainbowing, which means that we're looking through some clouds. Okay. So, subtracting the clouds out of there using this this processing part is good, but unfortunately this rainbowing means that there's some light clouds in there, and that's a problem. But it's better than this. This was, you know, not this, but let's see, where was I? Going back a ways.
Is there any way we can visit M46? Cosmic Lettuce is hinting that it's quite a nice cluster.
Yes, it is. And we can do M46, I think. And I believe that's in Puppis, correct?
I don't know.
You don't know? What do you mean you don't know? How could you
Well, don't
not?
you know?
Yes.
Ha.
Yeah. And
Puffis?
Puppis, I believe.
Puppis. Oh, Puppis.
Yeah. M46. NGC 2437. We find it, and it's over there, and it's this little cluster right there. And that's the one, if you recall, that I wrote up something online about, because it has this beautiful little planetary nebula in it. So let's go there, and let's hope the dome doesn't have to be moved. It may have to be, but we'll see. It may have to be.
John wants to know who helped you put all this together, or did you do it all yourself?
Well, I wish I had someone to help me.
That's what I figured.
I didn't have anyone to help me. I've been putting this all together for actually a couple years, and I didn't see first light until about a year and a half ago, and it was important to do it right, because you don't want to just start showing this thing, doing, you know, having the telescope go in, you know, any old place, you know. So, but that's okay. It is what it is. And let's do 15 seconds at 16,000 here. This is actually quite interesting, this cluster, because the cluster of stars is one distance away, and there's a planetary nebula that's in this cluster. Now, here's the weird thing about clusters. When you see a young cluster like this, or a cluster of stars, all right, like this one, which has this little planetary nebula in it, the first thing you have to do is move it over, because I need to get it a little bit better centered. First thing you notice is that when you have a cluster like this, it means it's all young stars. So how could all these young stars, actually have such a singular old star in it? You know, well, it can't. There's something not quite right. 20,000 at 20 seconds. Here we go. Right, and what it means is either that this violates all of our rules and understanding of how clusters are, or we're just seeing an illusion. Why? Well, because young stars don't produce planetary nebulae. They are young. They don't show the end of their lives to us like this. Not before they've all run their course, and we'll have multiple. Then at that point, we'll have multiple stars that are dying in this cluster, right? And see here, we're seeing that we have a planetary nebula right here in this cluster, and then a young cluster. So how could this star actually have died if it was born at the same time as these? The answer is it didn't. It's actually a lot closer to us than the cluster. The cluster is more than twice the distance away than this star. If we were heading toward the cluster, this star with the planetary would zoom by us, and we'd keep right on going. And I think it's pretty cool. You know, it's literally just essentially double the distance away from the star. We'd hit the star halfway to the cluster, and then the star would be in our rearview mirror, and the cluster would still be looming in the distance that we would be approaching. Really kind of neat, you know. So let's see here. If we just to do a little processing, which is kind of fun. Now you can see the cluster shows up really, really brightly now. Okay, you can see it, and it's a little. Again, it's a shell, and you'll notice that it's blue. Okay, kind of like your Cat's Eye Nebula that you like, Amanda. And this. Okay, sorry. I was just reading the chat here for a minute. I wasn't sure what I was looking at there. It's sort of like the Cat's Eye Nebula in that it's got this shell of oxygen-3, which is doubly ionized oxygen. And it's not oxygen-2. Oxygen-2 is singly ionized because oxygen-1 is the base state where there's no ionization. So you just have to get used to that terminology. And so this is the typical bluish color that we see in a planetary nebula. And it's really nice. It's a really pretty nebula. It's got a lot of character because it has this beautiful spherical shell, you know. So I really think it's just a gorgeous, I should say, dichotomy of seeing this young cluster with one star that's dying, supposedly almost in it, but it's actually, like I said, it's a lot closer to us than this cluster, which is a lot farther away. So hopefully that was a fun thing for you guys to see. I liked it, but then again, I'm a nut, and I'm okay with being a nut.
That's very pretty.
It was very pretty.
Very pretty picture.
Yep. And as you can see, you know, you don't see it here. You know, there's just no way. Actually, if we go to 4K mode, let's see if we can acquire it. Let's see if we can pull it out. Oh yeah, just barely. There it is. See it? Can you see it there?
What am I looking at?
Well, this is the, you know, we're looking at the cluster. We're trying to find the. We're trying to see the planetary nebula.
I don't see it.
Okay. Well, let's just go back for a second to our. See where it is there. Okay.
Mm-hmm.
And now we go back to our 4K mode shot. Right here.
I see that one.
See?
Mm-hmm.
Yeah, pretty cool. So you can see, I mean, this sort of simulates what you'd see in larger telescopes, right? So you can see how you're not going to, you're not going to be able to see something directly with your eye. Potentially, you're going to end up having to use this averted vision, to see things, which is fine. It's what happens. So I think I think we're looking at a pretty good rendering of that cluster. It looks good. So let's now go to our let's go to our
Bed?
no, let's go here. Why do you want to go? You can go if you need to.
No, I'll stay.
All right. I won't argue with you. So let's see now. I want to want to get some images back here of, well, that's Canis Major there. There's the heart-shaped cluster. These, see all these
Heart nebula?
No,
or
no,
just a heart-shaped cluster.
Heart-shaped cluster.
Ooh.
When you see this indicator in this program, in this little planetarium program, that little circled dotted circle, that's the indicator for a cluster. Okay, a little ellipse in red is a galaxy. So when we come down, for instance, and look here, right in the middle there, okay, that's a galaxy. All right, which is inside of NGC. It's actually NGC 2283, and we can check it out. I mean, it's small, but we can try it out. We may not see it, but we'll go. It's kind of low right now, but let's give it a shot. So here we go. Check out what we got. See what we can see. So we're moving. You can see the little star moving across there, so we know we're moving. Now it's refining and coming back. Bring up our telescope controls. And I know we're probably going to have to go this way. So I'm going to go this way. Okay. And now we'll do 20 seconds at 32,000. Why not? So off we go. And we're looking for this little tiny galaxy. Let's see what we get. Keep in mind, by the way, that the telescope lens on the outside is actually a little bit compromised right now. We actually have a little bit of frost on the inside edge of that lens, so we are a little bit compromised. So we're not perfect. Okay. Yeah, you can see some green here and some red. That's actually not nebula. That's actually indicator of clouds, unfortunately. So I guess that isn't going to work. So we're compromised to the point where we're not going to be able to see it, I don't think. So let me just go to our stellarium view. And let me back out here. You'll see we're actually kind of low to the ground here, All right, so let's do this. Let's do this. And yeah, we're definitely we're definitely in it, that's for sure. All right, let's just do this. I'm going to close out the evening with another view, a final view of the Orion Nebula. So let's go there now, and let's see what we got. All right, make sure that we're actually going to be good here.
This is beautiful.
Well, doesn't look right. Yeah, it's not looking right to me. Yeah, it doesn't look right. as I'll show you, do 10 seconds at 32,000 just for fun. You know, the problem is that I think we're compromised. Yeah, we're definitely compromised. You can see this strange coloration here. Yeah, that's definitely an indicator that we have some clouds in the area. So I'll probably go outside and be surprised to see that there's like clouds everywhere. You know. Also, you notice down here, you see that little spike? That indicates that the telescope is actually at the edge of the dome as well. So that could be responsible for making it look like there's clouds too. All right, well, that said, I think that it's probably a good stopping point, being that we've only gone about 3 or some odd hours.
4.
4 or some odd hours, and it's okay. I once I get going, you guys know how I am. I just I can't stop. You know, I just love I love what I do. I love what I do.
And it's contagious. And that's why people keep coming back.
I think that it's definitely, you know, well, I guess contagious is a good word. So, sadly, that's true. Well, hey, you know what? I mean, every clear night we're going to be streaming, because I'm inside, man. I don't have to be cold anymore. I'm also, you know, excited about it. And yeah, Chris is right. I mean, I'm sure I've got clouds too. But you know, I'm very pleased you guys once again have joined me, and I want to just go through the list again. We have 12 feet tall. We have Amol. We have City Lights. We have Cosmic Lettuce. We have Daryl, of course. We have Chris Elliott from Elliott Astro Imaging. We have Happy Mama. That's a new one.
Welcome.
Ian, yeah.
She's bringing brownies. She's good people.
Awesome. We have Ian McQueen, of course. We have James Dugan from Down Under. We have Justin T. Laura Hovey is still around. Thank you, Laura, for sticking around. We have Mark Rose, Mark the Shark. And we have Jello and Weird Guy, who's sitting there at the end with that his little acronym. You guys are fantastic. I want to thank you again as I already had thanked you for joining us before, and I'm thanking you once again.
And remember, don't just hit the subscribe button. Hit the little bell beside it, and that's when, as soon as Mark goes live, whenever it might be, you'll get a notification.
Oh yeah.
And you can come join us.
Yeah. And
subscribe is great, but the bell is what gives you the notifications.
Yes, that's correct. Yeah. And before we go, I'll just
tell a friend.
Yeah, please do. I'm gonna just take one more photo of this location. I've actually, like I said, this is the spectral system, and this is the camera, and you can see the to the right of the barrel of the telescope, you can see the edge of the spectral system there. So I'm gonna. It's either going to be that you'll either see that on the telescope, or you're going to see the large 5-inch refractor mounted up there. I could put them both, but I want to keep the other smaller telescope, which is also mounted here that you don't see in the view. I want to also put that up there and keep that on. But I'd waiting for my image here to show up. And it is not.
Oh no.
That's okay.
Why not?
I don't know. I mean, this image showed up.
Well, I want to see the image before we go.
Yeah, me too.
It's kind of a disappointing way to end the stream.
No, but that's okay. This is the spectral thing. I actually want to do one more thing that's a little bit different. We're going to come back to this. And what I'm going to do is I'm going to have our camera like here. All right. I'm going to move the camera here up a little bit. All right. And there we go. And then I'm going to come back to this. Actually, come back to this. And then come back to that. Like that. All right. And do this. I think we got, like I said, we got clouds, but that's okay. All right. Actually, no, I was going the right way. Go that way. And now I'm going to do a... okay, now I come back to this and do my photo that I wanted to do before. All right. Oh, okay. I see what's going on. Okay. I am unable to photograph anything here right now. I've got a camera card issue going on out in the dome, I guess. So that's no problem. Let's just see it on the regular 10 seconds at 32,000 here. Orion Nebula is going to be down below now. So, you know, all these stars are just a little too dim. So clearly we're getting issues. Yeah, as you can see. We have cloud issues. Not good. All right. All right, well, that said, this, well, effectively ends the stream tonight because we cannot go further when we can't fight the clouds. But thanks again for coming. I'm glad you enjoyed this. The only thing missing from our streams is the music, and that's coming soon. I tried to get to it today, but I was actually working on some other sequences to help sharpen up the presentation a little bit. So if anyone's interested in all the hardware integration that we've done here to make this all work, you can let me know. Now, we do have an email address for those of you interested. It's SkyTour Radio at kgraradio.com. SkyTour Radio, all one word, at kgraradio.com. And don't forget to listen to Amanda and I on starting at 8 o'clock on Sundays coming up for SkyTour Radio, a 2-hour broadcast now, not 1 hour. And you can...
We're starting an hour earlier. Oh my God, I hope I'm not late.
You're not going to be late. Or else it'll be your shortest debut as a co-host.
Debut?
Well, yeah, for the new year. So, no pressure. You'll be fine. And this weekend we're going to talk about, as I said, we're going to talk about Ultima Thule. We're going to talk about the New Horizons probe and where it's been, where it's going. We're going to talk about the Mars Insight lander. We're also going to talk about the Mars 2020 project, which is going to have a helicopter on Mars. And then we're going to talk about some astronomy things and some exoplanet stuff, because we do the exoplanet roundup at the beginning of every show. And then we have some astronomy topics. Maybe I'm trying to think about what we'll talk about for the astronomy topic. It's not like I have to write this out, because this is all stuff that I've been doing for so long. It's just, I could easily become, fixated on one thing. So I got to be really careful not to. But man, I'll tell you, it's a lot of fun. So, and if you guys got any suggestions, again, our email is skytourradio at kgraradio.com, and listen to us Sunday nights at 8. So you guys have a good evening. Thank you for dropping by and hanging with us. I'm going to go...
A very happy new year again to everyone. And yes, thank you for taking time out of the first day of the new year to spend with us.
Oh, absolutely.
We really appreciate it.
It was a really, really good time. And, thank you, Amanda, for putting the address in the chat.
Yeah, that's what I'm here for.
Yeah. Actually, James, the Dugan, I just had to tell you, the helicopter's already been tested in the same pressure environment as Mars, because JPL has a chamber that they can reduce the pressure in to simulate Martian pressure, and the helicopter flies just fine. So they've actually got a really nice setup there. Thing is, when you have less air, the reactions of the helicopter are a lot more slowed down. In other words, to stop, you have to push against more air to stop, for instance. And to fly, you got to push against more air to go up, of course. But when you're going forward, like toward a cliff or something, you have to start slowing down a lot sooner because there's so little air, there's no resistance, and so you can just plow right into the cliff. The fact that they can establish flight is already a solid, provable conclusion because they're doing it. There's a video actually. You can look at the helicopter flying in the 0.08% atmosphere of Mars. 0.08% of Earth atmosphere, and because they've reduced the pressure, it's pretty to watch it do it. But the trouble is, it's flying in that reduced atmosphere, but it's still operating under 1g. That is to say, the acceleration due to Earth's gravity. So, if anything, it's going to make the helicopter more squirrely on Mars. So, we'll see what happens. But boy, oh boy, it's going to be a lot of fun. We'll talk about this on Sunday, too. We're going to have a lot of fun. We're probably not going to go commercial-free anymore. We usually go commercial-free, but with a 2-hour show...
Not for 2 hours, no.
Yeah, no, we have to. We're going to have to. We need... we're going to have to allow KGRA to make some money on our show, so...
And I just put the link to KGRA in the chat. So again, that's 8 p.m. Eastern.
Yes, 8 p.m.
Eastern Standard Time.
Yeah. Very good.
Okay.
Awesome. All right, guys. Well, hey, thank you.
So I hope to see you guys Sunday. And worst case scenario, the next live SkyTour live stream.
Yeah, well, it's clear tomorrow. It'll be tomorrow, won't it?
Apparently.
I got a whole family of objects in this region I want to look at. We might start later, anyway, just to be able to allow for these objects to come up. But we'll see. We'll see. Anyway, thank you, guys. I will talk to you soon. And again, if you have any questions that we didn't get to, please send them to SkyTour Radio at kjradio.com. We'd be happy to answer them. Love to hear from you. And I will talk to you guys soon. So good night, all, and have a pleasant rest of the first day of 2019. Good night.
Make it the best year ever.
Good night, all.